Hello there, and welcome to Science for Sleep, where curiosity takes its time and science moves at the speed of calm thought. Tonight's quiet exploration begins right under your feet, not in a metaphorical way, but literally beneath you, stretching in every direction, curving gently away, hidden by distance and softened by the air you breathe. We live upon a planet that feels flat, steady, and endlessly broad. Yet the truth is far more intricate. The earth beneath you is not flat, not even perfectly round, and certainly not still. It is a body moulded by gravity, shaped by motion, slightly squashed, slightly uneven, but beautifully balanced in the cosmic dance that holds it together. So, as you settle in, perhaps under a blanket or beside the soft hum of night, I invite you to think about the surface that carries you. What is its true shape? And how do we even begin to describe such a thing when our senses can only touch a tiny patch of it at once? It's strange, isn't it, that we can live our entire lives walking across a planet without ever really seeing its form. From where we stand, the ground extends in a straight line. The horizon feels like a boundary, and everything above it hangs in the sky like a vast ceiling. It's no wonder that for most of human history the world felt flat. Our eyes are tuned to local geometry, not global curvature. The curve of the Earth is there always, but subtle, hidden by scale. You could walk for 1,000 kilometers, and the ground would never appear to bend away. Our daily experience is built from straight lines and right angles, not arcs and ellipses, and yet, out there beyond the edge of our sight, the surface gently curves back on itself, forming the enormous self-contained world we call home. Before we go any further, I want to ask you something simple. Where are you listening from tonight? Maybe you're somewhere high, where the air feels thinner, or perhaps you're close to sea level, near a coast, or in a quiet room miles inland. Wherever you are, the planet beneath you connects seamlessly with everyone else listening. One continuous, unbroken surface looping endlessly around itself. And that's the first quiet miracle of our world. No edges, no walls, just a sphere of rock, water, and air, turning slowly in the dark. It's hard to imagine such vastness when all we ever see is a horizon, a few kilometers away. But that horizon, as ordinary as it seems, is your first clue to the Earth's true shape. It curves gently downward because the planet itself is curving beneath it. If you've ever stood by the ocean and watched a ship disappear, you've seen the planet's curvature in motion. The hull vanishes first, then the sails or the upper decks, not because the ship is sinking, but because the surface of the water is curving away from you. For ancient sailors, this was one of the earliest hints that the world was not flat. But even that observation, clear as it is, doesn't capture the deeper question. The Earth's shape is not just about curves on the surface. Physics tells us it's about forces, mass, and balance. It's about gravity pulling inward, rotation pushing outward, and the delicate compromise between the two that decides what shape really means. Before the equations and satellites, before the words geoid or oblate spheroid ever existed, there was the simple question, why are big things round? Look at a drop of water. Floating free, it pulls itself into a perfect sphere. No corners, no edges, just the smallest possible surface for a given volume. That's the work of surface tension, a tiny scale version of gravity's grand design. On a cosmic scale, the same principle applies. When enough matter gathers in one place, gravity takes over and begins to mould it inward from all directions. At first, small bodies can resist. A pebble can be jagged, a mountain can stand tall. But as the mass increases, gravity's pull grows stronger, until the material can no longer hold itself in irregular shapes. The result is roundness, not by design but by necessity. The shape of a planet is gravity's way of achieving equilibrium. For the Earth, this equilibrium produces something close to a sphere, but not quite perfect. That's because our planet is not only heavy, it's also spinning. Every 24 hours, it completes one rotation, and that rotation creates a faint but persistent outward push. You can feel a trace of it if you imagine standing at the equator. There, you're moving at over 6,600 kilometers per hour as the planet turns. You don't feel that speed because everything around you is moving with you. The air, the ground, the oceans, but physically, it's happening all the time, and that motion matters. The faster a planet spins, the more it bulges at its equator. Gravity pulls everything inward, but the rotation slightly lifts the middle outward. The result is an oblate spheroid, a sphere flattened at the poles and widened around the waist. This bulge isn't enormous by human standards. The difference between the Earth's equatorial radius and its polar radius is about 21 kilometers. To put that in perspective, if you could somehow shrink the Earth to the size of a perfect globe in your hands, that bulge would be thinner than the coat of paint on it. Yet in physics, that tiny difference means everything. It tells us the Earth's rotation isn't just an abstract concept, but a physical sculptor, shaping the world we live on. The ground beneath your feet isn't simply there by coincidence. It's been moulded over billions of years by the invisible tug-of-war between gravity and motion. And motion, as it turns out, never stops. The Earth isn't a rigid ball. It flexes and wobbles, stretching and compressing under its own dynamics. Tides pull at it. The moon's gravity gently lifts and drops entire oceans, and even the solid crust shifts imperceptibly as mass redistributes across the globe. These changes are subtle, often just millimeters or centimeters, but they remind us that the Earth's shape is alive in a physical sense. It's not a fixed form like a sculpture, but a living equilibrium, constantly being rebalanced. Mountains rise and erode, glaciers melt and reform, ocean floors spread and collide. Every one of these processes changes the distribution of mass, which in turn alters the exact contours of the planet. What's fascinating is that physics doesn't treat the Earth's shape as a simple geometric question. It defines it through energy. The shape we see, and the one satellites measure, is the result of the Earth finding the lowest possible energy configuration under all the forces acting on it. Gravity pulls inward equally in all directions, rotation creates centrifugal effects that distort symmetry, and the internal flow of molten rock redistributes mass over geological timescales. Together, these produce the real, physical outline of the world, something that can't be drawn as a simple sphere or even as a smooth curve. It's more like a dynamic surface of equilibrium, a balance of inward and outward pulls. Now, while we can describe this in words, it's worth remembering that for most of human history, no one could see the planet as a whole. The first real glimpse of the Earth's shape came only a few decades ago, when spacecraft and satellites gave us that extraordinary image, a blue sphere suspended in black. But even that view, beautiful as it is, hides complexity. The photograph shows smoothness, but if you could strip away the oceans and atmosphere, you'd see a planet pocked with mountains, trenches and depressions. The difference between the highest peak and the deepest trench is over 19 kilometers. Against the planet's radius of 6,371 kilometers, it's a minor variation, less than 0.3%, but enough to remind us that round is only an approximation. The real shape is more nuanced, full of ridges and basins, places where mass is denser, and regions where the crust floats higher on the molten mantle below. Even the air above plays a part. The atmosphere clings to the Earth not as a perfect shell, but as a compressible fluid. It's thicker around the equator, thinner at the poles, shaped by the same rotation that deforms the ground. This adds another layer to the planet's figure, a faint halo of gas constantly shifting and bending light. When you look at the horizon, you're seeing through that layer, distorted slightly by temperature and density. The bending of a light through air can make the world seem flatter than it is, reinforcing the illusion that the Earth is a vast plane. It's not surprising, then, that early observers trusted their eyes more than unseen forces. It took physics to reveal that the shape we feel is not the shape that is. If you were to travel far enough, high enough, you could see it for yourself. At around 35,000 feet in the air, passengers on a clear day can detect the slightest curve along the horizon. At 100 kilometers beyond the Kármán line, it becomes undeniable, a dark arc against the deep blue of atmosphere. And from orbit, the full sphere emerges, not as a symbol or abstraction, but as a physical truth. The curved line isn't art, it's geometry revealed. It's the projection of a massive rotating body seen from outside its own surface. That sight changes something in the human mind. It reminds us that everything we know happens upon a curve, all history, all life, all motion, tracing paths across a tilted, spinning, bulging planet. But to physics, seeing isn't the whole story. The Earth's shape is also measurable in the invisible realm of gravity. Gravity doesn't care about colour or light, it follows mass. And when scientists map the strength of Earth's gravitational field, they find it varies from place to place. It's slightly stronger near the poles, slightly weaker near the equator, influenced by the equatorial bulge and the distribution of dense rocks below the crust. This unevenness defines what geophysicists call the geoid, the true physical shape of the Earth. Not as a solid surface, but as a surface of equal gravitational potential. It's what you'd get if you could spread the oceans evenly under gravity's influence, with no waves, no tides, no wind, just stillness. The result is a bumpy, lumpy, gently distorted sphere. The real equilibrium shape of our world. That invisible form tells the truest story of what Earth is, because it reflects both the pull of mass and the push of rotation at once. For a long time, it was impossible to know such things. We could measure mountains, map coastlines, and build globes, but we couldn't detect subtle changes in gravity from place to place. That changed with the advent of satellites like Grace and Gokes, designed to sense the faintest variations in gravitational pull as they orbit. These spacecraft send back data that reveal the Earth's shape not as a static geometry, but as a dynamic field. They show the rise and fall of mass as ice sheets melt, oceans shift, and tectonic plates drift. The shape of the planet, it turns out, is always in motion. Not because the rock itself flows freely, but because the energy inside and around it never stops adjusting. When we talk about the Earth's shape, we're really talking about the balance of forces that hold the world together. Gravity pulls toward the centre, rotation pushes outward, the sun and moon tug at the surface, and the planet's molten heart circulates heat that moves continents inch by inch. Every one of these effects adds a wrinkle to the Earth's form. Even temperature changes matter, expanding and contracting rock, swelling the crust microscopically. Taken together, they make the planet a living object in physical terms, a sphere that never quite sits still. And yet, for all this motion and complexity, there's something comforting in the stability we feel. The ground doesn't ripple under our steps, the sky doesn't twist before our eyes. From our scale, the world is steady, predictable, solid. That steadiness is gravity's gift, the quiet reason we can rest, build, and breathe without thinking about the immense mechanics unfolding beneath us. When you lie down and close your eyes, the weight you feel pressing you into the bed isn't just your body. It's the entire mass of the planet beneath you pulling inward, holding you against its surface with perfect consistency. That pull defines the meaning of down, and by doing so, it defines the shape of the world you stand on. So here we are, perched on a spinning oblate spheroid, flattened at the poles, stretched at the middle, wrapped in a shifting layer of air, all balanced on the invisible threads of gravity and rotation. You can't see that shape directly, but you experience it constantly. Every step you take, every breath you draw, happens within that curved space. The physics of the planet define not only its outline, but your sense of direction, motion, and even time. When we measure hours, we're really measuring rotation. When we define distance, we're tracing arcs on a curved surface. The world's shape is woven into everything we do, whether we think about it or not. And perhaps that's the quiet beauty of it. The real shape of the Earth isn't a mystery to solve once and forget. It's an ongoing relationship between forces, an interplay of mass, motion and time. It changes slowly but never stops changing. It's both fragile and resilient, precise and irregular, ordinary and extraordinary. Every pebble and mountain, every drop of water and gust of air belongs to that same physical whole. So when you think about the shape of the Earth, you're not just imagining a globe in space. You're considering the outcome of billions of years of physics in motion, the balance of a world that turns and holds itself together with quiet perfection. And as the night deepens and the planet spins once more beneath you, that same balance continues, invisible but constant. The surface curves gently away into the dark, ocean shifting in rhythm, gravity drawing every grain of sand toward the centre. Somewhere far above, satellites trace their silent paths, mapping the contours of a world we can't see from here, but live within completely. And as your thoughts slow, as your breath softens, you're part of that shape too, another moving element in the physics of a planet that never truly rests, only turns. When you look out toward the horizon, it's easy to believe the world is flat. Everything you see, every building, tree or stretch of land stands upon a surface that seems perfectly level. Roads vanish straight ahead. Water settles smoothly into lakes and oceans. The line where the sky meets the ground feels like the edge of something vast and flat. But this is not because the world truly is flat. It's because we are small. Our eyes evolved to make sense of immediate surroundings, not the scale of planets. The curvature of the Earth is so broad and gentle that, from where you stand, it disappears into invisibility. The human mind cannot sense a curve that extends over thousands of kilometres. It reads that immense arc as a straight line. That's why, to us, the world appears flat. Not because it is, but because we are too close to see its bend. Imagine standing in a massive field, perhaps a desert or a prairie, with no mountains or trees in sight. The land looks like a perfect plain, stretching infinitely in all directions. But if you could somehow rise upward, say by climbing a high tower, the horizon would begin to shift. It wouldn't extend farther. Instead, it would drop slightly below your line of sight. The higher you climb, the farther you see, but that horizon keeps curving away. This is the first quiet sign that the Earth is not flat. The drop of the horizon with altitude is measurable, predictable, and explained entirely by geometry. The Earth's curvature causes the surface to fall away from any given point at a rate of about 8 inches per mile squared. It's not enough to see when walking, but it becomes clear over great distances or heights. Long before satellites or space travel, people noticed this. Sailors in the ancient world saw ships disappear hull first beyond the ocean's edge. A slow, vanishing act that puzzled observers who believed in a flat sea. The simplest explanation, once one dared to think beyond appearances, was curvature. A spherical surface would naturally hide the lower parts of an object as it moved farther away. The higher portions would remain visible for longer, just as the masts of ships lingered after the decks had gone. This observation wasn't philosophy or faith, it was direct evidence. The horizon, calm and quiet, revealed the shape of the world without ever needing words. But even then, the truth wasn't easy to accept. The human experience of flatness runs deep. For early farmers, builders and travellers, the land behaved as though it were level. You could dig, measure and build without ever accounting for curvature. For those purposes, the Earth's shape was irrelevant. It was only when minds turned upward, to stars and distances, that the illusion began to crack. The ancient Greeks, meticulous in their reasoning, started to compare the geometry of the heavens to what they saw on the ground. When Aristotle noticed the Earth's shadow on the moon during a lunar eclipse, it was always round. No matter where or when the eclipse occurred, the shadow's curve remained the same. That was possible only if the Earth itself was round. A flat disk would cast an elongated or distorted shadow depending on the angle of the sun and moon. A sphere, on the other hand, would always project a circle. It's easy now to take that logic for granted, but in its time it was revolutionary. To say the Earth was curved meant reimagining everything about one's place in the cosmos. The ground beneath you was no longer an endless expanse. It was a surface wrapped around itself, a boundary that had no edge. The idea was so elegant, so mathematically consistent, that it slowly began to replace the flat intuition of daily life. Yet even as knowledge spread, the illusion of flatness persisted. Because when you step outside and look at the ground, the eye still tells the same story. The slope of a hill or the arc of a horizon can't reveal curvature at the human scale. The mind trusts what it sees, and what it sees is local. That's why physics matters here, because it lets us go beyond the limitations of sight. It offers tools to measure and model what the senses cannot grasp. Take gravity, for example. Gravity doesn't care about appearances. It follows rules that apply everywhere, from pebbles to planets. Its pull is always directed toward the center of mass. On a flat world, gravity would have to act in parallel lines, pulling objects straight down everywhere. But on a spherical world, gravity points inward, toward the center. You can feel this every moment of your life, even if you don't notice it. Stand at the equator, and gravity pulls you just as firmly as it does at the poles. But the directions of those pulls are not parallel. Each person on Earth stands downward toward a different point, yet all feel the same sense of up and down. The only way that can happen consistently is if the surface curves around a center. If the Earth truly were flat, gravity would behave strangely. Objects near the edges of a flat disk would not fall straight down. They would fall at an angle toward the center of the disk. Lakes would bulge, oceans would drift, and the direction of down would vary across the surface. But nothing of that kind occurs. Water finds its level, always perpendicular to gravity, and the sea does not slide towards some central point. Every local measurement, from a hanging plumb line to the tilt of a level instrument, confirms the same truth. Gravity pulls inward from all directions, not sideways or diagonally. That simple, invisible force reveals the planet's curvature more reliably than any picture could. For centuries, people tried to reconcile what they saw with what they felt. The tension between appearance and reality is not new. Even the earliest explorers sailing across vast oceans had to trust mathematics over instinct. When they followed a compass bearing for months and returned from the opposite direction, they proved through motion what their eyes could never show. The Earth loops back on itself. In physics terms, this means its surface has positive curvature. You can travel endlessly without finding an edge because there isn't one. The curvature closes in on itself, forming a continuous surface. It's worth pausing on how counterintuitive that really is. Our brains are designed for flat maps and straight paths. We imagine direction as a simple line from here to there. But on a curved surface, those lines wrap around. The shortest path between 2 points, a straight line in geometry, becomes a great circle on a sphere. Airplanes follow those invisible arcs, not to take detours, but because the curvature of the Earth makes them the most efficient routes. What looks like a curved track on a map is actually the straightest possible path through three-dimensional space. This is one of those moments where physics gently corrects perception, showing how geometry can deceive us. There's another reason the world feels flat. Compared to its size, we are unimaginably small. The Earth's radius is about 6,371 kilometers. If you could shrink it to the size of a smooth billiard ball, it would actually be smoother than the ball itself. The highest mountains and deepest trenches are insignificant at that scale. So when you stand on a patch of land, you're standing on a tiny segment of a vast curve, so small that it seems straight. It's like an ant walking along an orange. To the ant, the peel feels endless and flat. Only from far above could you see its roundness. We live in that same kind of illusion, one created by scale rather than deception. Still, perception isn't wrong so much as it's local. Physics builds bridges between what we see and what we can't. It tells us that curvature exists because matter bends space itself. Gravity isn't just a force pulling objects downward, it's the shape of space and time around mass. This means that when you walk across the ground, you're not moving over a flat plane but along a curve shaped by the planet's gravity. You don't feel that curvature directly, because your body and your environment follow the same shape together. Everything around you, air, trees, buildings, shares the same curved frame. Only when you step back in imagination or through science can you perceive that curvature as the outline of a sphere. The illusion of flatness also arises from the way light behaves in the atmosphere. When sunlight or starlight passes through air, it bends slightly due to refraction. That bending makes the horizon appear higher than it truly is. On a perfectly spherical Earth with no atmosphere, the horizon would drop more sharply with distance. The presence of air softens that curve, creating the subtle mirage that extends flatness beyond its geometric limit. This effect is why ships vanish more slowly than expected, and why sunrise and sunset occur a few minutes earlier and later than they would in a vacuum. The atmosphere bends light just enough to blur the curve, smoothing the transition between visible and invisible. It's a natural optical illusion produced by physics itself. To move from illusion to reality, scientists rely on measurement. The first accurate determination of the Earth's size came from a simple experiment more than 2,000 years ago. In ancient Egypt, a scholar named Eratosthenes noticed that on the summer solstice the sun stood directly overhead in the city of Syene, casting no shadow. Yet at the same time, in Alexandria, hundreds of kilometers to the north, vertical sticks did cast shadows. By measuring the angle of those shadows and knowing the distance between the two cities, he used geometry to calculate the circumference of the Earth. His estimate was remarkably close to modern values, differing by only a few %. Without leaving the ground, he had used physics and reasoning to map a planet. That experiment remains one of the most elegant demonstrations of how small observations can reveal vast truths. Eratosthenes didn't need satellites or telescopes. He needed sunlight, distance, and patience. The fact that the same sun could stand overhead in one place and angle differently in another was enough to prove curvature. It showed that the Earth's surface isn't flat but angled relative to the incoming light. Every degree of difference in that angle corresponds to a slice of the planet's arc. Multiply it around the full circle, and you have the planet's size. What's remarkable is that the result didn't just answer how big, but also confirmed what shape. Today, we've confirmed those findings countless times over. Satellites measure the Earth's radius to within millimeters. Lasers bounce off reflectors placed on the moon to refine the calculations. Spacecraft in orbit see the curve directly. Every method, optical, gravitational, or geometric, agrees on the same truth. The world curves gently, predictably, and perfectly according to the physics of a massive rotating sphere. Yet the illusion persists because perception doesn't update itself automatically. It remains anchored to what the eyes see. And so, in a way, living on Earth means living inside a kind of optical misunderstanding. We're surrounded by curvature but experience flatness. We're held by a round planet but see only straight horizons. Physics bridges that gap, offering not just facts but perspective. It lets us step back in imagination and see the bigger picture, to recognize that the flat field underfoot is one small piece of a vast curve wrapping around itself. This understanding doesn't change how the world feels, but it deepens the sense of where we are. The illusion of flatness becomes less a mistake and more a reminder that human perception is built for closeness, not for cosmic scale. As technology advanced, so did our ability to visualize that curvature in motion. Weather satellites, for instance, record the planet turning, clouds sweeping across a visible curve. Astronauts on the International Space Station see it constantly. The thin blue arc of atmosphere against the black of space, the clear boundary between day and night sliding across the surface. That boundary, known as the Terminator line, moves because of the planet's rotation, tracing out the geometry of a sphere every single day. The roundness of Earth isn't a matter of theory anymore. It's an observed physical reality, recorded in images and measurements every moment. Even so, understanding the real shape of the Earth requires looking deeper than the surface. The sphere we see isn't perfectly symmetrical. The equatorial bulge makes it slightly wider than it is tall. That distortion, caused by rotation, would not exist if the planet were flat. It's a direct consequence of motion acting on mass. Physics predicts it precisely, and instruments confirm it. Every deviation from perfect roundness matches what the laws of motion demand. The illusion of flatness collapses completely under the weight of consistency, and yet, there's something quietly beautiful about the illusion itself. It connects us to our scale, to the ground we walk on, and the perspective we live within. The flatness we feel isn't an error, it's a feature of our limited reach. It's what makes the planet feel vast, stable, and habitable. The curve hides itself just enough for us to build and move without noticing it. It's there, constant, patient, bending beneath our awareness. And when we finally see beyond it, when we imagine the world as a round, spinning body balanced in the void, the illusion doesn't vanish. It transforms into understanding. The transition from flat illusion to curved reality isn't just a change in knowledge, it's a change in scale. The closer we look, the flatter things appear. The farther we step back, the more curvature reveals itself. That relationship between distance and perception is built into physics itself. Space curves with mass, light bends with gravity, and our view of the universe depends entirely on where we stand. The same principle that hides the Earth's curvature also governs galaxies, black holes, and the fabric of space-time. We live on a curve within a greater curve, seeing only the parts we're built to see. So when you gaze at the horizon, whether it's over land, sea, or city, remember that its straightness is an illusion created by perspective and scale. The real world beneath that calm line is curved, rounded, and turning slowly under your feet. Every direction you look bends gently away from you, wrapping back to meet itself. You're standing not on a surface with edges, but on a small section of a vast sphere. A world whose shape has been revealed not by sight, but by understanding. The illusion of flatness is a reminder of our place within something larger. Not the end of the story, just the beginning of seeing more clearly. The curve of the Earth isn't something distant or abstract. It's beneath you, holding you steady as it spins. The flat world you feel and the round world that physics describes are the same place, seen through different lenses, one by instinct, one by knowledge. If you were to peel away all the oceans, all the mountains, every layer of air and soil, what you'd find at the heart of the Earth's roundness isn't a perfect sphere carved by chance, but something moulded by an invisible architect. That architect is gravity, the quiet blueprint maker that designs every large body in the universe, from the smallest moon to the largest star. Without it, there would be no curves, no centers, no balance. The entire cosmos would be a cloud of scattered dust, drifting aimlessly through space. Gravity is what gathers, shapes, and holds the matter that becomes worlds. Its touch is gentle and relentless, subtle and absolute. It's not loud or visible, yet it defines everything we see. And on the scale of planets, it's the reason the Earth takes the form it does. When matter accumulates, gravity begins to act not as a simple attraction between objects, but as a sculptor of form. Every atom, every grain of rock, pulls on every other. The more mass gathers, the stronger the pull becomes, and as it grows, the system seeks the most efficient way to distribute that force. In physics, that efficiency is expressed through symmetry. A sphere is the only shape where the pull of gravity is equal in every direction. Any protrusion or irregularity creates an imbalance. and over time gravity smooths it out. This principle, called hydrostatic equilibrium, explains why small asteroids can remain jagged and irregular while planets and stars become round. The difference is mass and the pressure it generates within itself. If you pick up a rock and look at its edges, you'll see the limits of gravity's influence on small scales. The rock's structure, defined by the strength of its bonds, can resist gravity completely. The forces between its atoms are far stronger than its own tiny gravitational pull. But if you take a mountain-sized rock, or better yet a moon-sized one, the story changes. As the object grows, its own gravity begins to crush the internal structure. The strength of materials can't withstand the inward pull. At a certain threshold, the object collapses toward a rounder shape. It might not become perfectly spherical right away, but given enough time and heat, gravity will continue to press, deform, and rearrange the matter inside until equilibrium is reached. At that point, all the forces balance. The inward pull of gravity is exactly matched by the outward pressure of material strength or internal energy. The result is roundness. This process doesn't require intentional guidance. It's a natural outcome of the laws of physics. Gravity is a universal tendency toward balance. You can think of it as nature's way of minimizing tension. A sphere is the simplest form that minimizes that tension everywhere at once. Every part of the surface is the same distance from the center, and every particle of mass is equally influenced by the rest. If the planet were shaped like a cube or a disk, the corners and edges would experience uneven forces, causing material to shift and collapse inward until the imbalance disappeared. Gravity has no preference for elegance, but it always chooses efficiency. A sphere is the most efficient way for mass to rest under its own pull. The Earth formed in this way more than 4.5 billion years ago, starting as a swarm of smaller bodies colliding in orbit around the young Sun. Those collisions generated heat, enough to melt rock and metal. Once molten, gravity had free rein. The liquid planet rounded itself out as material flowed inward and outward, settling into equilibrium. Heavier elements like iron sank toward the center. Lighter ones like silicates rose to the surface, and the planet cooled into layers: core, mantle, crust. What we stand on today is the hardened outer skin of that self-shaped sphere. But the shaping never really ended. The Earth's rotation, its internal convection, and its gravitational interactions with the Moon continue to refine its form even now. Rotation complicates gravity's simple blueprint, but it doesn't contradict it. The Earth spins, and because of that spin, not everything falls directly inward. At the equator, the outward push from rotation slightly counters gravity's pull. The faster an object rotates, the more pronounced this effect becomes. In the Earth's case, that outward force causes a subtle bulge around the middle. Gravity is still in control, but the planet's equilibrium must now account for motion as well as mass. The final result is a compromise, not a perfect sphere, but an oblate one. That balance is described mathematically through what's called the equipotential surface, a surface on which all points experience the same gravitational potential energy. On Earth, that surface is close to spherical, but stretched slightly at the equator. It represents the level at which gravity and centrifugal force balance exactly. The real surface of the oceans conforms to this equipotential shape, rising slightly higher around the equator where the outward push is strongest. The difference in height between poles and equator may sound small, only about 21 kilometers, but in planetary physics it's immense proof of motion's effect on form. Gravity alone would have made a perfect sphere. Rotation transformed it into something more complex, a sphere with a personality. Inside the planet, gravity continues to define structure. It keeps the dense metallic core compressed under enormous pressure, over 3 million times that of the atmosphere at the surface. It dictates how heat moves upward through convection, how tectonic plates float and drift, and how the ocean basins rest lower than the continents. Every mountain, every valley, every contour is a response to the balance between internal forces and gravity's pull. Even the air you breathe is shaped by it. The atmosphere grows thinner with height not because of distance alone, but because gravity holds the molecules close. The density decreases exponentially as you move upward, giving Earth that soft blue halo seen from space. Without gravity's blueprint, there would be no such gradient, no sky, no boundary between surface and space. When you think about it, gravity doesn't just create roundness, it creates orientation. Up and down have meaning only because of it. The direction we call down is always toward the planet's center. That's true everywhere, whether you're at the poles, the equator, or standing on a mountain ridge. Each point on the surface has its own local down, pointing toward the same center. This is what allows the curved surface to feel flat locally. To you, down is always beneath your feet. To someone halfway around the world, their down is in the opposite direction, yet they feel just as upright as you do. Gravity's symmetry ensures that no matter where you stand, you experience the same relationship between body and surface. If you were to visualize the strength of Earth's gravity across its surface, you'd find small variations caused by differences in density. Regions with heavy rock formations, like mountain ranges, exert a slightly stronger pull than areas above deep ocean trenches. These variations are tiny, but modern instruments can detect them. Satellites equipped with sensitive accelerometers map these changes with incredible precision. What they reveal is that gravity is not perfectly uniform, and therefore the Earth's shape isn't either. But those small deviations only highlight how gravity continues to shape the planet in fine detail. The overall blueprint remains the same, an equilibrium between inward pull and outward push, constantly maintained through the flow of matter and energy. One of the most fascinating aspects of this blueprint is how it connects scale to shape. Small bodies like asteroids don't have enough mass for their own gravity to overcome the strength of their materials. That's why they can remain irregular, even potato-shaped. But once an object reaches a few hundred kilometers in diameter, gravity begins to dominate. The internal strength of the material is no longer sufficient to resist collapse, and the object rounds itself. This threshold marks the boundary between irregular rock and spherical planet. It's a quiet rule of the universe. Once a body becomes large enough, gravity takes over as the ultimate architect. This idea extends beyond planets. Stars follow the same principle. Their immense mass causes gravity to compress hydrogen until nuclear fusion ignites. Even then, the shape remains spherical because only a sphere can maintain equilibrium between gravitational compression and outward pressure from heat and radiation. Galaxies too form roughly spherical halos of matter around their centers. Gravity's blueprint scales endlessly upward, always seeking symmetry, always turning mass into curves. On Earth, that same principle governs tides, those rhythmic rises and falls of the oceans caused by the gravitational pull of the moon and the sun. The oceans stretch slightly along the line connecting Earth to the moon, forming two bulges, one facing the moon and another on the opposite side. As the planet rotates, these bulges move around, creating the cycle of tides. It's gravity at work again, not just holding matter in place, but constantly adjusting it to maintain balance between competing forces. The blueprint is flexible. It accommodates motion, rotation, and interaction, yet it always returns to equilibrium. If gravity vanished for even a moment, that balance would dissolve instantly. The oceans would no longer cling to the planet. The air would drift away into space. The crust itself, freed from pressure, would fracture and float apart. The roundness of the Earth exists only because gravity never stops acting. It doesn't take breaks or rest. It's the one constant force keeping the world coherent. Even when we're not aware of it, it's present in every step, every fall, every breath. When you drop an object and watch it fall, you're seeing the same principle that shaped the entire planet. The same pull that draws a stone to the ground is the one that pulled molten rock into a sphere billions of years ago. What's remarkable about gravity's design is that it doesn't care about what something is made of. It acts on everything equally, based solely on mass. That universality makes it the most democratic force in nature. A feather and a mountain both follow the same rules. Their difference lies not in how gravity treats them, but in how other forces, like air resistance or rigidity, interact with that pull. When it comes to shaping worlds, those smaller forces become negligible. On planetary scales, gravity dominates completely. That's why the Earth, despite its mountains and oceans, remains fundamentally round. Those surface irregularities are nothing compared to the scale of its own pull. Over the course of geological time, gravity continues to refine the planet's form. Erosion wears down mountains, sediment fills basins, and mass redistributes until a kind of global equilibrium emerges again. Even major impacts like the one that created the Moon only temporarily disturb that shape. Afterward, the molten remnants cool and settle back into roundness. The blueprint holds, persistent and self-correcting. Understanding this quiet force doesn't make it feel any less mysterious. Gravity is still one of the most puzzling aspects of physics. We can describe how it behaves with incredible accuracy, but we still don't fully understand why it exists. Einstein's theory of general relativity describes gravity not as a force in the traditional sense, but as a curvature of space-time caused by mass. In that view, the Earth isn't held together by invisible strings of attraction. It's simply following the geometry of its own warped space-time. The surface curves because space itself curves. The planet is round because it exists within a curved field it creates around itself. The blueprint isn't drawn on a sheet of space. It is the sheet of space. This interpretation deepens the idea of shape. The Earth's roundness isn't just a property of matter, but of the geometry of the universe. When you stand on the ground and look up, you're not just standing on a surface shaped by gravity. You're standing inside the curvature that gravity produces in space-time. That curvature determines how everything moves, from falling apples to orbiting satellites. It defines not only the Earth's physical form, but the path of time itself at different altitudes. So the real blueprint of Earth's shape is written in a language that combines matter, motion, and geometry. It's a silent conversation between mass and space, carried on through equations and orbits, always seeking equilibrium. You experience it every moment without noticing, in the way your body feels weight, in the way the ocean lies level, in the way the sky curves around you like a vast dome. All of it is gravity, patiently doing what it has done for billions of years, drawing things together, balancing energy, shaping matter into curves, and as this pull continues, the planet holds its form, a quiet, spinning world moulded by invisible lines of attraction. The oceans stay in their basins, the air clings to the surface, and the curve beneath your feet remains steady. Above it all, gravity keeps the Moon in orbit, tides in rhythm, and your body gently anchored where you rest. Everything, from the faint pull on your arms to the outline of the entire world, follows the same quiet blueprint. When you picture the Earth turning, it's tempting to think of it as a simple spin, a smooth rotation that repeats endlessly, silent and unchanging. But rotation is far from a passive motion. It is a source of shape, energy, and balance. The world we live on is defined not only by its gravity, but by its movement through space. That movement is not just linear, it's rotational, constant, and measurable, transforming the very geometry of the planet. Everything you experience, day and night, weather patterns, tides, even the bulge at the equator, traces back to this unending spin. The Earth's rotation is not a backdrop to life. It is part of the physical framework that makes life possible. If the planet stopped spinning, nothing on it would remain the same. The air, the oceans, even the molten rock below would collapse into new patterns, guided by gravity alone. But rotation adds another force to the system, one that gently modifies how gravity acts. It's called the centrifugal effect, and though small compared to gravity's pull, it shapes everything subtly but persistently. Because the planet rotates once every 24 hours, every point on its surface moves with it. The speed depends on latitude. At the equator, where the circumference is greatest, the surface travels about 1,174 kilometers per hour relative to the planet's axis. Move north or south, and that speed decreases until it reaches zero at the poles. This difference in motion is one reason the planet is slightly flattened. The equatorial regions experience a faint outward pull from rotation, while the poles, where the outward motion is absent, feel only gravity's inward tug. Over millions of years, this interplay has sculpted the Earth into an oblate spheroid, wider at the middle and narrower from top to bottom. The centrifugal effect is small but consistent. At the equator, it reduces your effective weight by about 0.3%. You wouldn't notice it without instruments, but it's measurable. A person weighing 70 kilograms at the poles would weigh about 69.8 kilograms at the equator. It's not that gravity weakens there. Rather, part of its pull is counteracted by the outward push of rotation. The balance between those two influences defines not only the planet's shape, but also the equilibrium of its oceans and atmosphere. Water collects slightly higher around the equator, air moves differently with latitude, and the entire climate system evolves under the combined pattern of spinning and pulling. Rotation does more than alter shape, it organises motion on every scale. The air currents that form trade winds, the great spiralling storms, and the jet streams that steer weather across continents, all arise because the Earth turns. If the planet were still, the sun would heat the equator more than the poles, setting up a simple pattern of rising warm air at the centre and sinking cold air at the edges. But rotation complicates this symmetry. As the Earth spins, air moving north or south is deflected sideways, an effect known as the Coriolis force. It isn't a separate force in the fundamental sense, but a result of moving within a rotating frame of reference. To someone on the ground, it feels as though the wind curves naturally, but what's really happening is that the surface itself is turning beneath the air. This deflection organises the atmosphere into large circular patterns, giving rise to trade winds near the equator and westerlies in mid-latitudes. This same principle applies to the oceans. Currents that might otherwise flow straight from pole to equator instead spiral, creating vast gyres that transport heat and nutrients around the planet. The Gulf Stream, the Kuroshio Current, and countless others owe their trajectories to the rotation of the Earth. The planet's spin transforms what would be a simple pattern of convection into a complex dynamic circulation system that redistributes energy and shapes climate. Without it, weather would be static and extreme, blistering at the equator, frozen at the poles. The spinning Earth smooths those extremes, spreading warmth and maintaining the balance on which ecosystems depend. The rotation also gives rise to a phenomenon called the equatorial bulge. It's easy to imagine gravity alone pulling everything inward evenly, but the outward effect of spin causes the surface to expand slightly outward at the middle. That bulge changes the distance from the centre of the Earth to its surface, increasing it by about 21 kilometres at the equator compared to the poles. This difference means that the equatorial regions are farther from the planet's centre, where gravity is weaker. The two effects, outward push and increased distance, reinforce each other, reducing the net gravitational acceleration slightly. It's a small difference, but enough to be significant for precise measurements. Satellites orbiting the Earth must account for the planet's oblate shape when calculating trajectories, because that bulge alters the gravitational field just enough to shift an orbit over time. Rotation's influence doesn't end at the surface. Deep within the planet, the molten outer core circulates around the solid inner core, creating electric currents that generate Earth's magnetic field. That magnetic field, in turn, protects the atmosphere from solar wind and cosmic radiation. The rotation of the planet helps sustain that dynamo effect, maintaining a stable magnetic shield that has persisted for billions of years. Without rotation, the magnetic field might weaken or collapse entirely. exposing the atmosphere to erosion by solar particles. The existence of a breathable sky and the conditions that allow complex life to thrive are tied in part to this steady spin. Though we measure the day as exactly 24 hours, the planet's rotation isn't perfectly constant. It slows over time, ever so slightly due to tidal friction. The gravitational pull of the moon raises bulges in Earth's oceans, and as those bulges move, they drag against the planet's surface. That friction transfers angular momentum from the Earth to the moon, causing our planet's rotation to slow while the moon drifts gradually farther away. The effect is tiny. The length of a day increases by about 2 milliseconds every century, but it accumulates. Hundreds of millions of years ago, days were shorter, perhaps 22 hours long, and there were more of them in a year. Fossil corals and tidal sediments preserve that rhythm, revealing the story of a planet whose spin slowly unwinds as it interacts with its companion in space. This gradual slowing influences the shape of the Earth too. As the planet's rotation decelerates, the equatorial bulge relaxes slightly, allowing the globe to become marginally more spherical. The difference is imperceptible on human timescales, but across eons it matters. The balance between gravity and rotation shifts continuously, adjusting the equilibrium of the planet's form. Even the redistribution of mass caused by melting ice sheets and shifting tectonic plates feeds back into the system, changing the moment of inertia and subtly altering the spin rate. The planet's shape, its rotation, and its internal flow are part of one continuous feedback loop, each affecting the others over immense spans of time. Rotation also produces a slight wobble in the planet's axis, known as precession. The Earth doesn't spin perfectly upright relative to its orbit around the Sun. Its axis is tilted about 23.5 degrees, and that tilt slowly traces a circular path over roughly 26,000 years. The cause lies in the gravitational pull of the Moon and Sun on the Earth's equatorial bulge. That pull acts like a torque, causing the axis to sweep out a slow, graceful circle in space. The effect changes the timing of the seasons relative to Earth's orbit and contributes to long-term climate cycles. Over even shorter timescales, the planet experiences smaller wobbles called nutations and variations in rotation speed known as polar motion. These oscillations are minuscule but measurable, reminders that the Earth's rotation, though steady, is never completely uniform. All these motions together create what might be called the dynamic equilibrium of the planet. Gravity holds everything inward, rotation pulls outward at the equator, and external forces from the Moon and Sun modulate both. The result is a stable, constantly adjusting system. The stability is astonishing considering the scale of forces involved. The angular momentum of the Earth, its rotational energy, is enormous. To stop the planet's spin entirely would require an unimaginable amount of energy, greater than all the sunlight Earth receives in millions of years. That stability ensures the cycles of day and night remain dependable, a foundation for life's rhythms. Rotation also defines the passage of time in a very real sense. Our concept of a day arises from the period of one rotation relative to the Sun. Every clock and calendar is ultimately tied to that physical motion. It's easy to forget that timekeeping is based on the spin of a planet, but that's what underlies every hour and minute you measure. The world's rotation is both a physical and temporal anchor. Even atomic clocks, which count time using vibrations of atoms, are synchronized occasionally to stay aligned with Earth's slowing spin. When the planet drifts out of sync with our definitions of time, we add a leap seconds to bring them back together. It's a quiet acknowledgement that the passage of time itself is, in part, a consequence of a rotating world. From the perspective of physics, rotation is a form of stored energy. The Earth's rotation represents angular momentum that has persisted since the planet's formation. When the solar system was a disk of dust and gas, every particle orbited the young sun. As those particles collided and merged to form larger bodies, they carried their angular momentum with them. Because angular momentum is conserved, The resulting planet retained a spin. The direction of that spin and its speed were inherited from the swirling motions of the early solar nebula. Over billions of years, the same momentum continues, unchanged except for the gradual losses to tidal friction. The Earth's rotation is, in a sense, a memory of its origin, a remnant of the swirling cloud that gave birth to the solar system. That continuity connects the shape of the Earth to the history of the universe itself. The same laws that cause a collapsing cloud of gas to spin faster as it contracts, the conservation of angular momentum, apply to figure skaters pulling in their arms or to stars forming in distant nebulae. The spinning of our planet is a small, local expression of a universal principle. Rotation creates stability and shape wherever it occurs. The flattening at the equator, the gentle outward bulge, the predictable alternation of light and darkness, all are consequences of that ancient momentum still playing out today. If you could stand outside the Earth and watch it rotate from space, you would see more than just a spinning ball. You would see a planet whose every feature responds to its motion. The clouds trace bands that align with latitude. The oceans swirl in patterns driven by deflection, and even the flow of molten rock in the mantle aligns with rotational forces. The whole planet behaves like a gyroscope, maintaining its orientation as it moves through the solar system. That gyroscopic stability keeps the tilt of the axis steady enough for seasons to remain consistent. Without it, the planet's climate could vary chaotically, swinging from extreme cold to unbearable heat. The steady spin ensures moderation and continuity. When astronauts in orbit watch the world turn below, they're seeing this stability made visible. The rotation is smooth, silent, and majestic. The clouds drift, the continents slide slowly past, and the edge of the world curves away into night. What they see is the surface manifestation of deep physical order. Beneath that motion, inside the crust and the molten core, the forces of gravity and rotation keep everything balanced. The atmosphere doesn't fly off into space, the oceans don't pile up at one point, and the ground doesn't shift uncontrollably. The rotation doesn't tear the world apart because gravity holds it together with perfect restraint. And yet, balance doesn't mean stillness. The Earth's spin continually exchanges energy with everything around it. When wind blows eastward, it subtly transfers angular momentum to the planet. When ocean currents flow westward, they do the opposite. When ice accumulates at the poles or melts into the sea, it shifts the distribution of mass, slightly altering the rotation rate. The Earth adjusts instantly, redistributing motion so that the total angular momentum remains nearly constant. This responsiveness, this self-correcting precision, is one of the most remarkable aspects of a rotating world. It's as though the planet constantly fine-tunes its balance, ensuring that the spin continues smoothly no matter what happens on the surface. For scientists, measuring this rotation provides an immense amount of information. Instruments called ring laser gyroscopes and satellites equipped with inertial sensors can detect changes in the Earth's rotation down to fractions of milliseconds. These measurements reveal the influence of earthquakes, ocean tides, and even changes in atmospheric pressure. A powerful earthquake, for instance, can slightly alter the distribution of mass and speed up, or slow down the planet's rotation by a few microseconds. The entire planet behaves as a connected system, where motion, shape, and mass are inseparable. All of this makes rotation more than just a feature of the planet. It's part of its identity. Gravity provides the foundation, but rotation adds texture, variation, and rhythm. It explains why the equator bulges, why the climate moves, and why days unfold in a predictable sequence of light and dark. It defines the balance between rest and motion that makes Earth dynamic yet stable. The world's shape cannot be described fully without acknowledging that it's spinning. Without that motion, the blueprint would be incomplete. As the planet turns beneath you right now, you don't feel the speed. The air, the ground, and everything around you share the same rotation, so there's no sensation of movement. But the physics never stops. The centrifugal effect still lightens your weight slightly. The Coriolis deflection still guides the winds above you, and the gyroscopic stability of the whole planet continues to preserve its axis. Rotation is everywhere, woven into every quiet moment. It's the hidden rhythm that holds the world steady. And in that steadiness, the Earth keeps sculpting itself. The oceans shift minutely, the air flows in loops, the crust drifts over a molten interior that rotates differently beneath it. Even the core spins at a slightly different rate from the rest of the planet. A reminder that the Earth is layered in motion, not a single rigid body. All of these movements, large and small, combine into one continuous rotation that has lasted since the planet was born. The same spin that rounds the horizon and marks the passing of a day also keeps the entire structure in dynamic balance. As you sit or lie quietly, the planet turns beneath you, carrying you eastward at hundreds of meters per second. The stars outside seem still, but that stillness is an illusion created by distance. Everything in motion feels still from within. The only reason we can tell that the world rotates at all is because of the patterns it leaves, the alternation of day and night, the shape of weather, the physics of balance. The ground you trust as unmoving is part of a vast rotation, and that rotation is part of a larger motion still. The Earth orbiting the Sun orbiting the Milky Way, and the galaxy itself drifting through cosmic space. The planet's spin is one step in that hierarchy of motion, a single layer in an infinite chain of rotating systems, and yet all of it feels perfectly calm. The rotation of the world is so smooth, so consistent, that we don't sense the movement. We are, for all practical purposes, weightless passengers on a sphere of rock and water spinning quietly through the void. The balance between gravity and motion keeps everything in place, from oceans to atoms. The shape of the Earth, its gentle bulge, its steady curve, its slight tilt, all of it flows naturally from this single, continuous act of rotation. And as the Earth keeps turning, that motion continues to shape every part of its being. It holds the seas in their basins, directs the winds above, and balances the invisible forces that define its form. The world spins, gravity responds, and together they maintain the quiet symmetry that underlies everything. When we think of a sphere, we imagine perfection, a shape where every point on the surface lies at an equal distance from the centre. It's simple, complete, and balanced. But the Earth, as physics reveals, does not quite fit that idea. It's not a perfect sphere, but something more complicated, more alive in its geometry. Its roundness carries subtle asymmetry, a quiet distortion introduced by rotation and internal flow. That distortion makes it slightly flattened at the poles and wider across the equator, a shape known to scientists as an oblate spheroid. The words may sound abstract, but the meaning is straightforward. Gravity pulls everything inward toward the centre, while the planet's spin stretches it outward at the middle. Together they form a compromise, a balanced imperfection that defines the real physical shape of our world. At first glance, the difference might seem trivial. The equatorial radius of the Earth is about 6,278 kilometres, while the polar radius is roughly 6,357 kilometres, a difference of about 21 kilometres. Compared to the planet's total size, that's a mere fraction, only about 1 part in 300. If you could hold a scale model of the Earth in your hand, that bulge would be thinner than a layer of paint. Yet this small deviation matters enormously in physics, because it reveals the dynamic nature of the planet. The flattening isn't just a geometric curiosity, it's the visible record of balance between two immense forces, gravity pulling inward and rotation pushing outward. Gravity acts equally in all directions, seeking to pull mass toward the centre. If the Earth were stationary, that symmetry would produce a perfect sphere. Every atom would experience the same inward pull, An equilibrium would be achieved when the entire planet reached uniform potential energy. But the Earth doesn't sit still. It spins. And spinning introduces motion that resists inward collapse at the equator. The centrifugal effect of rotation is weakest at the poles, where the surface doesn't move relative to the axis, and strongest at the equator, where the surface speed is greatest. The result is that matter at the equator experiences a slightly reduced effective gravity, not because gravity itself weakens, but because part of its force is balanced by outward motion. Over billions of years, the planet reshaped itself until those opposing tendencies reached harmony. It helps to think of this balance in terms of energy. A planet in rotation contains both gravitational potential energy, which draws mass inward, and rotational kinetic energy, which resists compression. The shape of the planet minimizes the total energy of this system. If it were a perfect sphere, the equatorial regions would contain more rotational energy than necessary, creating tension. By bulging outward slightly, the planet redistributes that energy more evenly, achieving equilibrium. This balance is precise and self-sustaining. Any deviation would lead to a shift until the system settled again. In physics, this equilibrium shape is called the Maclaurin spheroid, a solution that describes how a rotating fluid mass behaves under its own gravity. The Earth, though not entirely fluid, behaves close enough to this model that the description fits remarkably well. To understand why the planet's crust doesn't simply resist this deformation, we have to consider how materials behave under long-term stress. Rock may seem rigid on human timescales, but under immense pressure and over geological epochs, it flows like an incredibly slow liquid. Deep within the Earth, the mantle, the layer between the crust and core, circulates with viscous convection currents. That slow movement allows the entire planet to adjust its shape gradually. When the bulge first developed, the material of the planet shifted over millions of years until the internal forces balanced again. The crust, being thin and brittle compared to the planet's radius, followed along. Even now, the redistribution of mass through processes like melting ice sheets or shifting tectonic plates causes minuscule changes in the planet's flattening. We can see evidence of this shape directly in how satellites move. The equatorial bulge slightly alters the gravitational field, making it weaker above the equator and stronger near the poles. Satellites in orbit feel this difference. Those passing over the equator tend to drift, their orbits precessing slowly due to the uneven distribution of mass. Engineers must account for this effect when designing long-term satellite trajectories. The International Space Station, for example, experiences tiny but continuous shifts that must be corrected periodically. These corrections are not arbitrary. They trace back to the same bulge that makes the Earth an oblate spheroid. The shape of the world literally affects how things move around it, from falling water to orbiting spacecraft. Even navigation on the surface is influenced by this flattening. The distance represented by 1 degree of latitude varies slightly between the equator and the poles. Because the Earth is wider at the equator, each degree there covers more ground than at higher latitudes. Surveyors and cartographers account for these differences in mapping systems, using mathematical models called reference ellipsoids to approximate the true shape. The most widely used model today, known as WGS84, underpins the global positioning system. Every GPS receiver, whether in a phone or a satellite, relies on an oblate model of the Earth to calculate position accurately. The flattening of the planet, subtle as it is, has become part of our daily lives in ways most people never think about. The physical cause of this flattening lies in the interplay between rotation and internal structure. The Earth's rotation rate and its internal density distribution determine how pronounced the bulge becomes. If the planet rotated faster, the flattening would increase. For instance, Jupiter, which spins once every 10 hours, exhibits a much more noticeable bulge, about 10% wider at the equator than at the poles. Saturn's is even greater, its gaseous form stretched by rapid rotation into a visibly oblate shape. The Earth's slower rotation produces a smaller but still measurable effect. The difference demonstrates how universal the principle is. Rotation inevitably leads to flattening whenever gravity binds a rotating mass together. Internally, the density of the Earth varies dramatically from core to crust. The dense iron-nickel core contributes most of the planet's gravitational pull, while the lighter silica mantle and crust provide structure. This layered density affects how the planet responds to rotation. Because the core is so dense, it contributes strongly to the overall gravitational field, keeping the bulge moderate rather than extreme. If the Earth were less dense inside, the same rotation speed might cause a greater flattening. The specific combination of mass, spin, and internal composition creates the unique shape we observe. It's a delicate equilibrium where each layer of the planet participates in maintaining the whole. Even the oceans reflect this geometry. Their surface aligns with what physicists call an equipotential surface, the level at which the combined effects of gravity and centrifugal force balance perfectly. That surface is not a simple sphere, but one that mirrors the planet's oblate shape. This means that the level sea isn't uniform everywhere in space, but follows the curvature of the planet's potential field. Water naturally finds this balance, flowing until its surface lies perpendicular to gravity's pull at every point. From orbit, the oceans form a slightly thicker band around the equator, following the same outward bulge as the solid Earth beneath them. The entire planet, both rock and water, shares this flattened symmetry. The concept of flattening may sound purely mathematical, but it has practical implications for nearly every branch of Earth science. Meteorology, for example, depends on understanding how the equatorial bulge affects atmospheric circulation. Because the equator is farther from the planet's centre, the gravitational acceleration is slightly weaker, allowing air to rise more easily. This contributes to the formation of persistent equatorial convection zones and influences the global distribution of winds. The same effect helps define the boundaries of jet streams and the placement of weather systems. Even the motion of ocean tides is subtly affected, since the distribution of water mass interacts with the planet's shape and rotation. To measure flattening precisely, scientists use a combination of satellite geodesy and ground-based observations. Laser ranging to satellites, radio tracking, and gravity mapping missions like GRACE and Geodesy have revealed the Earth's shape in astonishing detail. They show that the flattening is not perfectly uniform. Local variations in mass distribution cause slight deviations from the ideal ellipsoid. Mountains, ocean trenches, and variations in crustal thickness create small regional differences. The overall pattern, however, remains consistent, a smooth transition from pole to equator, the gentle consequence of a spinning world. It's important to understand that the flattening is not static. It evolves over time. The planet's rotation rate changes minutely due to tidal interactions and internal mass movements, and those changes feed back into the equilibrium shape. As glaciers melt and water redistributes, the load on the crust shifts, altering the balance of mass between poles and equator. Measurements over the past decades show that the Earth's flattening has been decreasing slightly, a result of polar ice loss and the gradual slowing of rotation. The planet is, very subtly, becoming more spherical as it adjusts to a changing distribution of weight. The scale of these adjustments is beyond ordinary perception, occurring over thousands of years, but they remind us that the Earth's form is dynamic, not frozen in time. This constant refinement extends deep below the surface. The mantle flows slowly under the planet's rotation, responding to pressure differences caused by flattening. These flows, though incredibly slow, redistribute heat and mass, which in turn affects how the crust deforms. The interplay between solid mechanics and fluid motion ensures that the Earth's shape always matches its internal and external forces. In that sense, the planet behaves like a self-correcting system. Whenever stress builds in one region, it's eventually balanced by flow elsewhere. Flattening isn't just a static property, it's part of a living balance between motion and matter. When we apply the same principles to other celestial bodies, the universality of the process becomes even clearer. The Moon, which rotates much more slowly relative to its size, is nearly spherical. Mars, with a rotation rate similar to Earth's, shows a comparable degree of flattening. The faster spinning gas giants, Jupiter and Saturn, exhibit extreme oblateness. Even stars flatten when they spin quickly enough, their equators bulging outward under the centrifugal influence. Everywhere in the universe, rotation and gravity conspire to produce the same geometry. The numbers differ, but the outcome is the same pattern, a sphere distorted slightly by motion, caught between symmetry and spin. To visualize this, imagine a drop of water spinning in microgravity. Without container walls or external interference, the droplet forms a perfect sphere at rest. Start it spinning, and the equator widens as the poles flatten, the surface adjusting instantly to balance centrifugal and gravitational effects. The drop becomes an oblate spheroid, precisely like the Earth. The only difference is scale. What happens in seconds for a drop of water happens over billions of years for a planet. The physics is identical. The equations that describe one describe the other. The flattened Earth is not an imperfection, but an expression of equilibrium. The outward motion at the equator and the inward pull toward the centre find a stable compromise, one that preserves the planet's balance through all its internal and external influences. The numbers that describe this shape, the equatorial and polar radii, the flattening ratio, the gravitational harmonics, are not just technical data. They're the coordinates of harmony and motion. Every part of the planet participates in maintaining this form, from the flowing mantle beneath to the quiet air above. If you could stand somewhere beyond the Earth, far enough to see it whole, that bulge would be invisible to your eye. The planet would appear perfectly round, its blue oceans and white clouds smooth and unbroken. Only through measurement and mathematics could you detect its true outline. That's the beauty of physics. It reveals the hidden details that sight alone cannot. The shape of the world, with its gentle flattening, is a story told not by appearance but by balance. As the Earth continues to rotate, its flattened shape persists, maintained by the same forces that created it. The oceans flow around the equatorial curve, the atmosphere circulates within its boundaries, and satellites trace paths adjusted by its subtle asymmetry. The planet's form is both a record of its past and a living reflection of its present motion. When we look at the Earth from space, the first thing we see is blue. Oceans cover more than 70% of the planet's surface, stretching endlessly, reflecting light, hiding everything below. From that distance, the blue looks uniform, smooth and simple. It suggests balance, a perfect surface gently wrapping around a sphere. But the reality beneath those waters is anything but uniform. The oceans conceal a landscape more rugged than any on land. Trenches deeper than mountains are tall, ridges that run for tens of thousands of kilometers, plateaus and plains shaped by pressure and heat. The surface of the sea may seem like a single curved skin, but beneath it lies a world of immense variety. And even there, gravity plays its quiet role, shaping not just the form of the solid Earth, but the liquid layer that moves above it. To understand what lies beneath that calm blue surface, it helps to think of the planet not as divided into separate layers of land and sea, but as one continuous body, with the oceans simply filling the lower regions of its outer shell. The line between ocean and continent is not a boundary between worlds, but part of the same global structure. The seafloor is made of crust, just like the continents, though it is thinner, denser, and younger. It forms constantly at mid-ocean ridges, where molten rock rises from the mantle and cools as it spreads outward. Over millions of years, that crust moves away from the ridges, slowly descending back into the mantle at deep trenches where tectonic plates meet. This motion, the slow breathing of the planet's surface, reshapes the entire geometry of the Earth from below. The shape we see from above is not static. It's a dynamic balance of uplift and subduction, creation and destruction, driven by the same internal forces that once moulded the planet into a sphere. Beneath the oceans lies the mid-ocean ridge system, a continuous mountain chain that circles the globe like a seam. It rises, on average, about 2.5 kilometers above the surrounding seafloor, yet it remains hidden under thousands of meters of water. The ridges are where new crust forms as molten basalt wells up from the mantle. As the material cools, it solidifies into rock, creating a new piece of the planet's skin. This process, known as seafloor spreading, is slow but relentless. A few centimeters per year, roughly the rate at which fingernails grow. Yet over millions of years, it rearranges continents and redraws the planet's surface. The Atlantic Ocean, for example, is widening because of spreading at the mid-Atlantic ridge. Each centimeter adds up, changing the distribution of mass and subtly altering the Earth's rotation and gravitational field. The shape of the Earth is therefore connected not just to its external forces, but to the unseen churn beneath the water. The seafloor, though unseen by most, plays a major role in how the planet's gravity field behaves. Where dense rocks lie beneath, gravity is slightly stronger. Where deep trenches or lighter sediments exist, it weakens. Satellites that measure gravitational variations can detect these differences even through thousands of meters of ocean. Using such measurements, scientists have mapped the ocean floor in exquisite detail, revealing mountains, valleys, and fractures invisible to optical instruments. Gravity itself becomes a tool for vision, translating subtle variations in pull into images of structure. What these maps show is that the ocean basins are not smooth bowls but intricate landscapes, as complex and varied as the continents. At the deepest points of the oceans, such as the Mariana Trench in the western Pacific, the seafloor lies nearly 11 kilometers below the surface. The pressure there exceeds 1,000 times that at sea level. These trenches mark places where one tectonic plate slides beneath another, plunging into the mantle. They are the deepest scars in the planet's crust, boundaries where surface and interior meet in constant motion. The material that sinks eventually melts and rises again elsewhere, fueling volcanic arcs and mid-ocean ridges. Every part of this system contributes to the ongoing redistribution of mass. It's slow, invisible to casual observation, but powerful enough to shift the Earth's moment of inertia and, over long time scales, slightly change its rotation rate and flattening. Beneath the uniform blue, the machinery of the planet continues, indifferent to the calm appearance above. If we could remove the water and expose the seafloor to air, we would see a world more dramatic than any landscape on land. There would be towering ridges stretching across entire ocean basins, cliffs taller than Everest, and vast plains dotted with seamounts, undersea volcanoes that rise thousands of meters but never break the surface. Many of these seamounts are extinct volcanoes, remnants of ancient eruptions that once poured lava onto the ocean floor. Some eventually grow high enough to pierce the surface, forming islands. Others remain submerged, shaped by currents and covered with sediment. Together they form part of the planet's rough texture, the unseen geometry that contributes to its gravitational balance. This unevenness affects more than geology. The shape of the seafloor influences how water moves across the planet. Ocean currents are steered by the contours below, guided through channels and around ridges. Deep water flows, driven by differences in temperature and salinity, follow these paths like rivers through valleys. The planet's rotation adds further complexity, deflecting currents and creating gyres that circulate heat across the globe. The entire ocean system, from surface waves to abyssal currents, functions as a dynamic layer responding to both the planet's shape and its motion. The uniform blue we see from above is a field of constant adjustment, balancing energy, mass, and momentum in a way that keeps the planet stable. To the eye, water seems weightless, but in reality it adds immense mass to the planet's surface. The oceans contain about 1.4 billion cubic kilometres of water, weighing roughly 1.4 quintillion tons. That mass, moving and shifting, affects the Earth's gravity field and even its rotation. When large volumes of water move, through tides, currents, or seasonal changes, they alter the distribution of weight, causing the planet's figure to deform slightly. This deformation is elastic but measurable. Satellites like GRACE detect it as tiny fluctuations in the gravitational field, showing how the oceans breathe with the tides. These constant adjustments illustrate that the shape of the Earth is not a fixed geometry, but a living equilibrium, flexing in response to the movement of water and air. The topography beneath the oceans also influences how light and heat are absorbed and distributed. The uneven surface creates variations in depth that determine how sunlight penetrates and how temperature layers form. Deep trenches and basins act as reservoirs for cold, dense water, while shallow continental shelves collect warmth and nutrients. These thermal gradients contribute to global circulation patterns that move energy from the equator toward the poles. Over time, this exchange affects climate stability, weather systems, and even the shape of the ice caps. The distribution of heat in the oceans feeds back into the dynamics of the planet's form by shifting mass through melting, expansion, and contraction. When we describe the Earth as round, we tend to think of it as a single, smooth entity. But the roundness exists only on average. Locally, the planet is full of deviations, bumps, dips, and asymmetries. The ocean's surface, though smooth to the eye, follows these irregularities precisely. The level of the sea isn't the same everywhere. It rises slightly over regions of greater mass and falls where mass is lower. This effect, caused by variations in gravity, means the true shape of the ocean's surface, known as the geoid, mirrors the hidden contours of density below. The difference between the highest and lowest points of the geoid can exceed 100 meters, even though the visible surface appears flat. The oceans, far from masking the planet's irregularity, reveal it through the way they curve and tilt under gravity's influence. To understand this, consider that gravity is not constant across the Earth. It varies because the planet's density varies. Under the oceans, where the crust is thinner and denser, gravity is stronger. Over continental regions, where the crust is thicker but less dense, gravity weakens slightly. Water responds to these differences by adjusting its level. Where gravity is stronger, the ocean piles up a little higher. Where it's weaker, it sits lower. The result is a surface that's constantly in motion yet always in balance. A perfect expression of how invisible forces shape visible form. The uniform blue, when measured carefully, turns out to be an intricate relief map of the planet's interior. Modern instruments have made it possible to see these variations with extraordinary precision. Satellite altimetry, which measures the height of the ocean surface relative to a reference ellipsoid, can detect changes as small as a few centimeters. Combining these measurements with gravity data reveals the underlying structure of the planet: ridges, trenches, and even massive features buried deep below sediment. Through physics, the invisible becomes visible. We can now see that the Earth's roundness is not simple symmetry, but a balance maintained through constant adjustment between solid, liquid, and gravitational forces. The connection between the oceans and the planet's shape goes deeper still. The movement of water affects how the solid Earth behaves. When large ice sheets melt, the loss of weight at the poles allows the crust to rebound upward, a process known as isostatic adjustment. This, in turn, redistributes mass and subtly changes the planet's gravitational field. Similarly, when sediments accumulate in river deltas or along continental margins, their added weight deforms the crust below, pulling that region of the surface slightly downward. Over time, these changes modify the Earth's figure on scales of millimeters to centimeters per year. They're small but cumulative, and they remind us that even the most stable parts of the planet are in motion, responding to the balance of mass above and below. If we think of the oceans as a mirror, reflecting the shape of the planet's gravitational field, we can see how intimately connected every part of the system is. A change in one region, melting glaciers, shifting currents, or rising temperatures, echoes through the entire structure. The water level in one ocean basin affects not only the coastlines nearby, but the equilibrium of the whole planet. The redistribution of mass can even alter the position of the rotation axis slightly, shifting the geographic poles by a few centimeters each year. This phenomenon, known as polar motion, shows that the Earth's shape is constantly adjusting to maintain balance under changing conditions. Beneath the uniform blue, the planet is alive with movement that transcends what the eye can see. Deep below the seafloor, the mantle continues its slow convection, circulating heat from the core outward. That heat drives the movement of tectonic plates, which in turn create the ridges and trenches that define ocean basins. The entire system operates over timescales so vast that it seems static to us, yet its consequences are immense. As plates shift, continents drift, and ocean basins open or close, the distribution of mass changes again, altering not only geography but gravity itself. Every rise or fall of the seafloor changes how the Earth spins, redistributing angular momentum between the crust and the fluid outer core. The planet, through all these processes, maintains its balance while never truly resting. The deeper one looks, the more the illusion of simplicity dissolves. Beneath the blue lies a landscape of motion and equilibrium, shaped by forces that act across every layer of the Earth. Gravity provides the blueprint, but pressure, temperature, and density fill in the details. The crust flexes, the mantle flows, and the water above conforms perfectly to the surface of equal potential that those forces create. From space, the oceans look smooth, but they are the exact opposite, the most accurate reflection of the planet's uneven reality. Their surface may appear still, but it is in constant dialogue with the mass beneath. And yet, in that complexity, the balance holds. The oceans remain where they are, the seafloor continues to shift in silence, and the planet keeps its steady curve. The uniform blue is an illusion born of distance, a colour that hides both chaos and order beneath. Every wave, every current, every hidden mountain contributes to the planet's shape. The Earth is not smooth or simple, but it is coherent, its motion and form tied together by gravity's quiet precision. The surface of the Earth, though smooth from space, is in truth a landscape of extremes. It is easy to mistake the planet for a uniform sphere when seen from afar, but when you stand upon it, you realize that it is far from even. Mountains rise into the cold upper air, trenches descend into darkness miles beneath the ocean, and between them lie vast plains, deserts, forests, and basins. These features make up the uneven Earth, a world carved by time and motion, moulded by forces deep within and influences far above. Every peak and valley is a record of the planet's long struggle between gravity's pull and the energy that pushes back against it. If the Earth were perfectly rigid, if its materials never yielded or moved, it would be nearly spherical, shaped only by gravity and rotation. But the planet's crust is thin and mobile, its mantle soft on geological timescales, and its surface continuously reshaped by the slow movement of tectonic plates. Those plates float on the underlying mantle, driven by convection currents that rise from the heat of the core. Where they collide, mountains form. Where they pull apart, rifts and trenches open. Over millions of years, these motions rearrange continents and oceans, adding texture to what gravity tries to smooth. The Himalayas, the Andes, the Rockies, and the Alps all owe their existence to this process. They are places where plates have collided, where the crust has buckled and folded under immense pressure. In the Himalayas, the Indian plate continues to push northward into the Eurasian plate, raising the highest peaks on Earth. That collision began around 50 million years ago and still continues today, at a pace of a few centimeters per year. Each earthquake in that region is a reminder that the process hasn't stopped, that the mountains are still rising, slowly, almost imperceptibly. Gravity resists their height, pulling constantly downward, eroding peaks through wind, water, and ice. But the tectonic push below replenishes what erosion removes. The result is a balance, a dynamic equilibrium where uplift and erosion counter each other over time. Even the tallest mountains, magnificent as they are small compared to the size of the planet. Mount Everest reaches about 8.8 kilometers above sea level, which sounds immense until you compare it to the Earth's radius of over 6,300 kilometers. The tallest mountain is only about 1,000th of the planet's radius, a microscopic bump on a planetary scale. If you reduced the Earth to the size of a billiard ball, its surface would be smoother than the ball's. The irregularities that dominate our view of the world fade to near nothing when viewed from afar. This is gravity's quiet triumph. No matter how powerful the forces of uplift and fracture, they cannot break its overall symmetry. Mountains add texture, but they never change the roundness of the whole. Yet while gravity keeps the planet broadly spherical, it is those irregularities that give the world its character. Mountains redirect winds, shape rainfall patterns, and define the flow of rivers. They act as boundaries for ecosystems and barriers for species. They influence how air circulates, how clouds form, and how water returns to the sea. Their presence affects everything from the path of weather systems to the course of evolution itself. In physics, mountains might seem insignificant, but in the context of life, they are essential. Below the oceans, the story continues in the opposite direction. Trenches mark the deepest parts of the planet's crust, places where one tectonic plate sinks beneath another into the mantle. The Mariana Trench in the western Pacific is the most famous of these, descending nearly 11 kilometers below sea level. It is a narrow crescent-shaped scar in the seafloor, formed where the Pacific plate slides beneath the smaller Mariana plate. The pressure at its bottom is unimaginable, more than 1,000 times the atmospheric pressure at sea level, yet even there, the rock slowly deforms, sediments accumulate, and life persists. The trench is part of the planet's mechanism for recycling its crust, pulling old, dense material downward to make way for new crust elsewhere. These deep trenches and high mountains are opposites in elevation, but they are connected parts of the same global process. When mountains rise, mass is added above the surface. When trenches deepen, mass is drawn below. The planet adjusts constantly to maintain its equilibrium. Gravity ensures that every excess of height is countered by an equivalent depression elsewhere, keeping the total balance of mass consistent. This balance is subtle and complex, influenced by density variations and the elasticity of the crust, but it's what allows the Earth's overall shape to remain stable despite constant surface change. If you could strip away the oceans and observe the planet's surface in full, the contrast between mountains and trenches would appear dramatic. The difference between the highest point on land and the deepest ocean floor is nearly 20 kilometers, but even this vast range represents only a small fraction of the planet's scale. In physical terms, the Earth's surface deviations are remarkably small compared to its size. It is a rough sphere, but a sphere nonetheless, where irregularities are smoothed by gravity and time. Still, those irregularities matter for understanding the planet's physical shape in detail. The gravitational field is not uniform because mass is not distributed evenly. A mountain range adds extra mass in one region, strengthening gravity slightly there. A trench removes mass, weakening it. These variations create small but measurable distortions in the planet's gravitational potential. The true physical shape of the Earth, defined by that potential, is not smooth but lumpy. Scientists call this the geoid, a surface of equal gravitational potential that defines where water would settle if it could flow freely under gravity alone. The geoid follows the highs and lows of the planet's mass distribution, mirroring mountains and trenches in invisible form. Mapping this uneven field requires extreme precision. Satellites equipped with sensitive instruments can detect changes in gravity as small as 1 part in a billion. By measuring how their orbits vary as they pass over different regions, scientists reconstruct a detailed picture of the planet's mass distribution. The result is a model of the Earth that includes all its irregularities, the high ridges, the deep trenches, and the variations in density within the crust and mantle. This model reveals that the planet's gravitational field is strongest over dense continental roots and weakest over deep ocean basins. It shows how mountains have deep foundations known as isostatic roots, extending far below the surface to balance their height above. The crust behaves like an elastic plate floating on a denser fluid, adjusting its depth according to its mass. This balance, called isostasy, is another form of equilibrium shaped by gravity. Imagine a block of ice floating in water. The higher the ice rises above the surface, the deeper it extends below. The same principle applies to mountains. Their visible peaks are supported by unseen extensions of low-density rock reaching deep into the mantle. The Himalayas, for instance, have roots extending roughly as far below the surface as their summits rise above it. This balance keeps the crust stable and ensures that the planet's shape remains smooth at large scales. Where the crust is thinner, such as beneath ocean basins, the denser material lies closer to the surface, producing deeper depressions. The interplay between height and depth, density and buoyancy, gives the Earth its complex but coherent form. Over time, erosion wears down mountains, carrying their material toward the sea through rivers and glaciers. Those sediments accumulate in lowlands and ocean basins, gradually filling depressions. Gravity drives this process just as it drives everything else. The movement of sediment is a transfer of potential energy toward equilibrium. Every grain of sand, every drop of water participates in the global effort to balance the planet's surface. When erosion lowers a mountain, the crust responds by rising slightly, a process called isostatic rebound. The same mechanism operates in reverse when ice sheets melt, allowing the land beneath to lift upward as the weight is removed. These adjustments continue for thousands of years, showing how responsive the Earth is to the forces acting upon it. The uneven Earth is therefore not a flaw in its shape, but an expression of its dynamics. Each mountain range, each trench, and each plateau is evidence of motion, the slow movement of energy and mass seeking balance under gravity. Even the continents themselves are temporary configurations, floating on a mantle that shifts and flows. Over the planet's long history, mountains have risen and vanished, oceans have opened and closed, and the face of the world has been remade many times. Yet through all this, the underlying shape remains consistent, a curved, slightly flattened sphere, maintaining equilibrium while evolving in detail. This constant remodeling has another consequence. Because the distribution of mass changes, so too does the planet's rotation. When mass moves closer to the axis of rotation, the planet spins slightly faster, much like a skater pulling in their arms. When mass moves outward, rotation slows. The melting of polar ice, for instance, redistributes water toward the equator, changing the moment of inertia and causing the rotation to adjust. These shifts are tiny, milliseconds of difference in a day's length, but they reflect the planet's responsiveness to its own unevenness. The shape of the Earth and the rhythm of its rotation are inseparable, both governed by the same principles of physics. The uneven surface also influences how we experience gravity. A person standing at high altitude is farther from the planet's center, and therefore experiences slightly weaker gravity than someone at sea level. The difference is minute, but measurable. Instruments sensitive enough can detect that gravity is weaker at the top of a mountain than at its base. Similarly, gravity is slightly stronger over dense mountain roots than over deep ocean trenches. These small variations matter for precise navigation, satellite positioning, and geophysical modelling. They also remind us that the pull we call down is not uniform. It depends on both the planet's shape and its internal structure. On a planetary scale, these irregularities are tiny, but they tell a story of continuous adjustment. The Earth's crust, mantle, and core are all in motion, and the surface reflects that motion. Mountains rise, trenches deepen, and the balance shifts. But gravity and rotation maintain the planet's coherence. The uneven Earth is not static chaos. It is dynamic order, where every height and depth serves a role in the global equilibrium. When we study these details through the lens of physics, the world becomes even more remarkable. Its apparent irregularity conceals perfect consistency in the rules that govern it. The same equations that describe the bulging of the equator explain the formation of mountain ranges and the sinking of ocean plates. Everything follows the same logic: matter responding to force, energy seeking balance, gravity maintaining curvature. The surface of the Earth, with all its roughness, is simply the outer expression of those laws in motion. From orbit, the planet's unevenness disappears, smoothed by distance. The roundness dominates, and the details fade into colour and light. But if we could magnify the view, if we could peer beneath the blue and the green, and into the rock below, we'd see the subtle interplay of uplift and erosion, density and buoyancy, pressure and release. The surface is a living record of forces that never cease, each mountain a frozen wave in a sea of rock, each trench a doorway into the depths where the crust returns to its origin. And so the Earth, imperfect in its details but perfect in its balance, continues to evolve. The unevenness that defines its surface ensures that the planet remains active, its shape refreshed by motion, its mass constantly redistributed. The tallest mountains and deepest trenches are the punctuation marks of that story, the visible signs of an invisible process that never ends. The uneven Earth is not a deviation from the ideal, but the realization of it. A world where gravity, pressure, and time create form through perpetual movement, where balance exists not as stillness but as continuity. Beneath your feet, that process continues even now. The crust drifts imperceptibly. The mantle circulates. The mountains rise by fractions of a millimetre each year. Above it all, the atmosphere responds, shaped by the terrain below, distributing heat and motion in patterns that echo the structure of the solid Earth. The uneven planet breathes through these motions, steady and slow, keeping its shape while never remaining the same. The curvature you can't see from where you stand and the ruggedness you can, both are expressions of the same quiet physics. When we speak of the shape of the Earth, we often imagine a smooth globe, an even surface wrapped neatly around its centre. But this picture, as comforting as it is, hides a deeper and more accurate truth. The real physical shape of our planet is not defined by its visible surface, nor by the outline we see in photographs from space. It is defined by gravity itself, by the way mass is distributed within the planet, and how that distribution shapes the field of force that holds everything to its surface. The result of that invisible pattern is something called the geoid, a concept that might sound abstract but represents the truest possible description of the Earth's form. It's not a geometric shape, not a sphere or ellipsoid, but a surface that traces equal gravitational potential everywhere on the planet. In other words, it's the shape the oceans would take if they were perfectly still, untroubled by winds, tides, or currents, responding only to gravity and the rotation of the Earth. To imagine the geoid, you have to shift the way you think about shape. Instead of picturing hills and valleys in terms of elevation above sea level, you must think of them in terms of gravitational potential. The amount of work it would take to move a small mass from one point to another within the Earth's gravity field. On a perfect sphere of uniform density, that potential would be identical everywhere, producing a smooth, simple surface. But the Earth is far from uniform. Its crust varies in thickness, its mantle contains regions of higher and lower density, and its rotation adds another layer of complexity. Because of these variations, gravity's pull is not equal across the planet. It's slightly stronger in some regions, weaker in others, tilted or distorted depending on the distribution of mass below. The geoid is the surface that perfectly balances those variations, the level at which gravitational potential is constant. To understand what that means in physical terms, think of a body of water. Wherever water can move freely, it will flow from regions of higher gravitational potential to lower potential, until it finds equilibrium. That equilibrium surface, where the water stops moving, defines part of the geoid. The same principle applies to the entire ocean. Every molecule of water aligns itself with the gravitational field, forming a surface that, while appearing flat to the human eye, actually bends and dips according to the underlying mass of the planet. When scientists measure sea level, they are in essence measuring this equilibrium surface. But because the Earth's gravity is not uniform, sea level is not the same everywhere. The geoid undulates gently, rising in some areas and falling in others, reflecting the subtle variations in the planet's gravitational pull. These undulations are not trivial. The difference between the highest and lowest points on the geoid can exceed 100 meters. That might not sound dramatic compared to mountain heights or ocean depths, but remember that this variation exists entirely within the invisible world of gravity. The surface of the geoid is as smooth as the calmest ocean, yet its shape captures the planet's mass distribution with exquisite precision. It is the blueprint of the Earth's gravity, a quiet mirror of its internal structure. To map this invisible surface, scientists rely on satellites that orbit the planet and measure tiny changes in gravitational acceleration. One of the most important missions to do this was GRACE, the Gravity Recovery and Climate Experiment, launched in 2002. GRACE consisted of 2 satellites flying in tandem, measuring the distance between them with extreme accuracy. As they passed over regions of stronger gravity, the leading satellite was pulled slightly ahead, increasing the distance between the two. Over weaker regions, the distance decreased. By recording these minuscule changes, scientists could infer variations in the gravitational field. Over time, those data built a detailed map of the geoid, a representation of how gravity changes across the globe. Later missions such as Geodesy, the Gravity Field and Steady-State Ocean Circulation Explorer refined that picture further. Geodesy measured gravitational gradients directly, allowing for even greater precision. The result was a global model of the geoid so detailed that it could detect mass changes from melting ice sheets, shifting ocean currents, and even variations in air pressure. These measurements revealed that the Earth's gravity field is not static but dynamic, changing as mass moves across the surface and within the planet. The geoid, therefore, is not a fixed shape but one that subtly evolves over time, tracking the living pulse of the Earth. Understanding the geoid has profound implications for science and technology. It provides the foundation for all height measurements on Earth. Every altitude, every elevation map, every mountain peak labelled with a height above sea level, all a reference to the geoid. Without it, sea level would be an arbitrary concept, inconsistent from place to place. The geoid gives that concept meaning, defining a common baseline tied to gravity rather than geography. It allows geodesists and engineers to measure distances with precision, ensuring that construction, navigation, and mapping all align with the planet's true physical field. The geoid also helps scientists study the Earth's interior. Because gravity depends on mass, variations in the gravitational field reveal differences in density below the surface. For example, regions where the geoid rises slightly indicate areas of higher mass concentration. Dense mantle plumes or thick crustal roots beneath mountain ranges. Areas where the geoid dips suggest lower density, thinner crust, less dense rock, or even hot buoyant mantle material. By analysing these patterns, geophysicists can infer the structure and dynamics of the Earth's interior, mapping features that lie hundreds or even thousands of kilometres below the surface. The physics behind these variations is straightforward but profound. Gravity is the sum of all the tiny pulls from every particle of mass within the planet. If more mass lies beneath a given point, gravity there is stronger. If less mass lies beneath, it's weaker. The Earth's rotation complicates this picture, adding a centrifugal component that varies with latitude. The combined effect of these influences produces a gravitational potential that is not perfectly symmetric. The geoid traces that potential, forming a three-dimensional map of balance. It's the most accurate physical representation of what shape means for a planet whose surface is in constant motion. One of the most fascinating aspects of the geoid is how closely it aligns with the surface of the oceans, yet how completely it diverges from the geometric shapes we use to describe the Earth. When we say the Earth is an oblate spheroid, we're describing an idealized figure, an ellipsoid that approximates the average curvature of the planet. But that ellipsoid is smooth and mathematical, a reference model for calculations. The geoid, by contrast, is real. It includes every bump, dip and asymmetry caused by the planet's mass distribution. It's as if the ellipsoid were a blank canvas, and the geoid were the textured painting laid atop it. The deviations between the two can be visualized as colours on a map. Warm tones where the geoid rises, cool tones where it falls, revealing a pattern that mirrors the hidden anatomy of the planet. For instance, the geoid is higher over regions like the Indian Ocean and the Western Pacific, where dense material beneath the crust increases gravitational pull. It's lower over areas like the South Pacific and parts of the Atlantic, where the underlying mantle is lighter. These features correspond not to surface elevation, but to deep structure, connecting gravity's variations to the behaviour of the mantle itself. In this way, the geoid becomes a kind of X-ray of the planet, a map not of what we see, but of what we're standing on. The study of the geoid also reveals how interconnected Earth systems are. When glaciers melt, the loss of ice changes the distribution of mass, causing local variations in gravity. The geoid adjusts accordingly, rising where mass decreases and falling where water redistributes. These changes can be measured over time, providing direct evidence of how the planet responds to climate processes. In Greenland and Antarctica, for example, satellite data show the geoid lowering as ice melts, while the surrounding oceans rise slightly to compensate. This dynamic behaviour illustrates that the shape of the Earth is not fixed even over human timescales. It shifts, however slowly, with every change in the balance of mass. The concept of the geoid might seem intangible because it deals with potential energy rather than physical form, but it is intimately connected to everyday experience. When you pour a glass of water, the surface naturally settles into alignment with the local geoid. That's what level truly means: alignment with an equal potential surface. The spirit level used in construction, the plumb line hanging from a ceiling, even the definition of vertical and horizontal, all rely on this principle. We live within the geoid every day, moving across it, building on it, and trusting it to define what flat means in a world that is anything but flat. From a broader perspective, the geoid links the Earth's internal structure to its external form. The distribution of mass deep within the planet determines the shape of its gravitational field, which in turn shapes the surface and the movement of water and air above it. The atmosphere follows the same gravitational contours as the oceans, forming pressure systems that respond to the planet's underlying mass distribution. The result is a subtle but real connection between geology and climate, a reminder that everything on Earth, from wind to stone, participates in the same gravitational framework. The precision required to study the geoid pushes the limits of measurement. Satellites track their positions to within millimeters, radar altimeters measure ocean height with centimeter accuracy, and complex mathematical models integrate data from millions of observations. The resulting maps are some of the most detailed representations of the Earth ever created. They reveal a planet that is neither simple nor static, but complex, dynamic, and interconnected. Each contour on the geoid corresponds to the sum of all the forces acting within and upon the planet: gravity, rotation, density, and motion, frozen into a single continuous surface. To visualize it, imagine peeling away the land and sea, leaving only the invisible scaffold of gravitational potential. What would remain is the geoid, a quiet, undulating shape hovering in space, following the planet's true field. It would look smooth to the eye, but in its details would lie the entire story of the Earth's mass and motion. Every rise and dip would mark a place where the planet is denser or lighter, thicker or thinner, heavier or more buoyant. It would be the purest expression of balance, the mathematical heart of the Earth's physical existence. What makes the geoid remarkable is that it doesn't just describe where things are, it describes how they move. Because gravity dictates motion, the shape of the geoid determines how water flows, how air circulates, and how satellites orbit. It defines the paths of rivers, the tilt of lakes, and the direction of ocean currents. Even the orientation of sea level relative to continents depends on it. The invisible shape beneath our feet controls the visible patterns above. Understanding it allows us to predict how the planet will respond to change, how ice melting in one hemisphere might raise water levels in another, or how mantle convection might alter gravity's pull over centuries. The more precisely we measure the geoid, the more we see its importance in everything from navigation to climate science. Modern GPS systems, for example, correct for the geoid's undulations to ensure that altitude measurements correspond to physical sea level rather than an idealized ellipsoid. Oceanographers use it to calculate currents, knowing that water flows along lines of constant potential. Geologists study its long-term variations to understand how the mantle shifts beneath continents. The geoid serves as the common language of these disciplines, the shared reference that links the planet's visible form to its invisible forces. And though the term might sound abstract, its meaning is deeply grounded in physical reality. The geoid is simply the surface where gravity and rotation reach equilibrium, the surface on which everything that can move eventually will rest. It's the true shape of the Earth, not because it's visible, but because it's the only shape that fully reflects how the planet's mass, motion, and energy interact. Every other description, the perfect sphere, the oblate spheroid, the rough terrain, is an approximation of that underlying balance. As our understanding deepens, we find that this balance is not unique to Earth. Every planet and moon has its own geoid, its own equilibrium shape defined by gravity and rotation. The differences among them tell stories about their internal composition and history. Mars's geoid, for example, shows large anomalies caused by ancient volcanic provinces. The Moon's reveals the impact of massive basins filled with dense material. Each world's geoid is a fingerprint of its evolution, a record written in gravity rather than stone. On Earth, the geoid continues to change. As ice melts, water redistributes, and the planet's rotation evolves, the gravitational field adjusts, and the equilibrium surface shifts. These changes are slow but relentless, measured in millimeters per year, yet over time they reveal the planet's responsiveness to every process that unfolds upon it. Beneath the steady rotation, the constant pull of gravity, and the apparent permanence of land and sea, the true physical shape of the Earth is always rewriting itself, shaped by motion, mass, and the delicate balance between them. And from this understanding comes a deeper realization. The geoid is not separate from us. We live upon it, measure ourselves against it, and rely on it for orientation and balance. Every structure built on Earth, from a simple stone wall to a spacecraft launch pad, depends on this invisible shape. It defines the meaning of level, the direction of vertical, and the relationship between every point on the planet's surface. Beneath the oceans, beneath the continents, beneath the quiet motion of air, the geoid endures as the foundation of all form, the invisible surface where physics and geometry meet. If there is a single thread that ties together every understanding we have about the Earth's shape, it is measurement, the quiet art of turning the invisible into something known. From the first shadows cast by ancient sticks to the sophisticated satellites orbiting far above the clouds, humanity's knowledge of the planet's form has always depended on our ability to measure what cannot be seen directly. The curve of the Earth, the bulge at its equator, the undulations of the geoid, and the subtle drift of continents all become real through numbers. Without measurement, even the simplest truths of our world would remain hidden within the illusion of flatness and stability. To measure the invisible is to give shape to reality itself. Long before modern science, people measured the world in the only ways they could, through sight, distance, and repetition. Early sailors noted how ships vanished over the horizon hull first. Surveyors in ancient times tracked the changing angle of stars across the sky. Each observation offered a fragment of understanding, a glimpse of the curve that lay beneath their feet. But the first true attempt to measure the Earth's size with precision came from a single observation of sunlight more than 2,000 years ago. Eratosthenes of Cyrene, a Greek scholar working in Egypt, noticed that at noon on the summer solstice, the sun shone directly into a deep well in the city of Syene, illuminating the water at the bottom. Yet at the same time, in Alexandria, several hundred kilometers to the north, the sun cast a shadow. By comparing the angle of that shadow to the distance between the two cities, Eratosthenes calculated the circumference of the Earth. His result, roughly 40,000 kilometers, was astonishingly close to modern measurements. That simple experiment, performed with no instruments more advanced than a stick and a ruler, revealed the scale of the planet. It showed that careful observation could reach beyond the limits of perception, translating the motion of light into the geometry of a world. Eratosthenes measured not what he could see, but what he could infer, and in doing so, became the first person to quantify the invisible curvature of the Earth. The logic behind his method remains as elegant today as it was then. By comparing two perspectives on the same event, the hidden shape emerges. Centuries later, as navigation improved and maps grew more detailed, new forms of measurement refined this picture. The invention of the sextant allowed mariners to determine latitude by measuring the angle of celestial bodies above the horizon. The establishment of precise timekeeping, through the creation of accurate clocks, made it possible to measure longitude as well. These advances turned the planet into a coordinate system, a grid of invisible lines that could be traced across oceans and continents. But even then, the true shape of the Earth remained uncertain. Was it a perfect sphere, or was it flattened? The difference was small, yet scientifically profound. In the 17th century, Isaac Newton predicted that the Earth, being a rotating body, must be slightly flattened at the poles. His reasoning followed directly from physics. Rotation would cause an outward centrifugal effect, greatest at the equator, reducing gravity's pull there and allowing the surface to bulge outward. The planet, he argued, must therefore be an oblate spheroid, wider than it is tall. To test this idea, expeditions were sent to different parts of the world to measure the length of 1 degree of latitude, the distance required for the angle of the sun or a star to change by 1 degree. If the planet were a perfect sphere, that distance would be the same everywhere. But if Newton's prediction was correct, the distance would be shorter near the equator and longer near the poles. Two great expeditions were organised in the 1730s, one to Lapland in the Arctic Circle, and another to Peru near the equator. The results were clear. The arc of 1 degree was longer in the north than in the tropics, confirming that the planet was indeed flattened at the poles. These measurements, made with chains, angles, and telescopes, settled a question that had lingered for generations. They transformed Newton's theoretical reasoning into empirical truth, grounding the shape of the Earth not in imagination but in data. The invisible forces of gravity and motion had found their reflection in numbers measured by human hands. Over time, these methods grew more precise. Triangulation became the foundation of geodesy. the science of measuring the Earth's shape, orientation, and gravity field. By constructing networks of triangles between known points, surveyors could determine distances and angles across vast regions with remarkable accuracy. Entire nations were mapped in this way, one triangle at a time. The Great Trigonometrical Survey of India, begun in 1802, was among the most ambitious of these efforts. It took more than 70 years to complete and covered thousands of kilometres. The surveyors, often working in brutal heat and difficult terrain, measured with such precision that their results later helped confirm the planet's flattening ratio. Their work was a triumph of persistence and mathematics, turning the Earth's surface into a grid of measurable reality. Yet, for all its success, traditional surveying faced limits. The curvature of the Earth meant that over great distances, measurements could never be perfectly straight. The line of sight bent with the horizon, and even the atmosphere refracted light, distorting angles. To go beyond those limits, scientists turned to the sky itself. Astronomical observations provided fixed reference points far beyond the planet, allowing positions on Earth to be determined relative to the stars. The combination of terrestrial and celestial measurements gave rise to the first accurate global models of the Earth's shape. By the 20th century, the development of radio waves and later satellites transformed the art of measuring the invisible. Radar and laser systems allowed distances to be measured with centimetre accuracy. The launch of artificial satellites in the late 1950s provided new tools for geodesy. As satellites orbited, their motion was influenced by the Earth's gravitational field. By tracking their positions over time, scientists could infer variations in gravity, and thus in the planet's mass distribution. What began as the work of surveyors on the ground expanded to include entire networks of orbiting instruments, turning the planet itself into a laboratory for measurement. The principle behind these modern methods is simple but profound. Gravity governs motion, so by observing motion, we can infer gravity. Satellites follow paths determined by the Earth's gravitational field, and any deviation in that field alters their trajectory. By monitoring those tiny deviations, we can map the invisible contours of gravity with incredible precision. Missions like GRACE and Geodesy made this possible. GRACE, by measuring the distance between two satellites with laser accuracy, detected changes in the gravitational field caused by movements of water, ice, and rock. Geodesy, equipped with ultra-sensitive accelerometers, measured the gradients in gravity directly. Together, these missions revealed the Earth's true physical shape, the geoid, in unprecedented detail. But measuring the invisible isn't just about mapping the planet's overall form. It also means observing its changes. The Earth's mass distribution shifts constantly as water moves between oceans, atmosphere, and land. Ice melts and refreezes, tectonic plates drift, and the mantle convects beneath the crust. Each of these processes alters the gravitational field slightly. By tracking those changes, scientists can monitor climate patterns, study groundwater depletion, and even detect earthquakes indirectly. Gravity becomes not just a static force, but a dynamic record of planetary life. The precision required for these measurements is staggering. The GRACE satellites could detect changes in gravity equivalent to moving a mass of a few hundred tons, the weight of a large ship, anywhere on the planet. Yet they did so from an altitude of hundreds of kilometres. This sensitivity allows scientists to see the invisible motion of mass on scales impossible to detect by any other means. When glaciers in Greenland lose ice, the change is reflected in the data. When large reservoirs fill or empty, or when vast underground aquifers are drawn down by human use, the redistribution of mass shows up in gravity's quiet adjustments. The invisible becomes measurable, and through that, knowable. Every measurement adds to a picture of the planet that is both stable and alive. The average shape remains constant, an oblate spheroid defined by rotation and gravity, but within that framework, subtle changes ripple across time. Measuring those ripples connects physics to history. The melting of polar ice affects not only sea level, but also the distribution of mass, altering the rotation rate slightly and shifting the position of the poles. These effects are minute but real, and only by measuring the invisible can they be seen. It's remarkable that all of this, the planet's shape, its gravity field, its motion, can be studied from distances of thousands of kilometers using light, radio, and mathematics. Yet the principle is as old as Eratosthenes' shadow. By comparing differences in time, distance, and angle, we reveal the structure hidden behind appearances. Modern measurement simply extends that logic to a scale unimaginable in the ancient world. Where once we measured shadows on the ground, we now measure the deflection of satellites in orbit. The continuity between the two is not just historical but conceptual. Both are acts of translating geometry into knowledge, of connecting what we can perceive to what we can't. Measurement also teaches humility. No matter how precise our instruments become, the planet remains richer and more complex than our models can fully capture. Every refinement reveals new irregularities, new layers of motion. The more closely we look, the more the boundaries between known and unknown blur. The geoid, once thought to be the final expression of the Earth's shape, turns out to be just one level of understanding. Beneath it lie deeper variations, changes in the mantle, flows in the outer core, that subtly alter the gravitational field. To measure them requires not only better tools, but deeper insight into how the planet works as a whole. The pursuit of these measurements continues to evolve. New satellite systems use quantum sensors that can detect gravitational variations with unprecedented accuracy. Ground-based instruments called superconducting gravimeters record tiny fluctuations in gravity caused by tides, rainfall, and even atmospheric pressure changes. Together, these technologies form a network that continuously monitors the planet, turning the invisible into data. Every second, those instruments capture the rhythm of the Earth's mass, its oscillations, shifts, and rebalances, providing a living record of its shape in motion. What's remarkable about measuring the invisible is that it transforms our relationship with the planet. Once, the Earth was something to be looked at, mapped, and crossed. Now, it's something to be sensed and understood through the most delicate of forces. Gravity becomes a language, one that speaks softly but reveals everything. By learning to measure it, we listen to the planet itself. We learn where its mass moves, how it breathes, how it changes through time. Each data point is a whisper from the Earth's interior, a trace of its continuing evolution. And yet, even as the instruments grow more precise, the purpose remains the same as it was for Eratosthenes standing in the sunlight of Egypt, to connect what we can observe to what lies beyond observation. Measuring the invisible does not only tell us about the Earth, it tells us about the limits of our perception and about the power of reasoning to extend those limits. The curve of the planet, the invisible field of gravity, the shifting balance of its mass, all of these exist whether we see them or not. Through measurement, we bring them into awareness. The story of measuring the Earth's shape from shadows to satellites is one of persistence. Each generation adds precision, building on the tools and ideas of those before. The journey from sticks and wells to laser altimetry and gravitational mapping spans thousands of years, yet it's guided by the same curiosity, the desire to know the shape of the world we stand on. Every improvement in measurement sharpens that image, bringing us closer to the truth that the planet is both perfectly balanced and perpetually changing. And as we continue to refine our instruments, as quantum clocks and gravitational interferometers extend our reach, the invisible becomes ever more tangible. We begin to see the Earth not as a static form, but as a system of flows, of mass, energy, and motion, woven together by gravity's constant pull. The act of measurement reveals that the shape of the world is not a boundary but a process. a continuous adjustment of equilibrium unfolding beneath our awareness. Even now, as satellites orbit above and sensors monitor below, the planet keeps moving, its balance shifting fractionally, its invisible field breathing with time. Every change, every motion, every fluctuation in density leaves a trace that instruments can record. To measure the invisible is to witness that ongoing dialogue between gravity and form, a dialogue that defines not just the Earth's shape, but the quiet physics that holds it together. And as the data continues to come in, as we watch the invisible patterns unfold, we realize that the measurement itself is part of the process. The instruments we build, the models we refine, the questions we ask, all become extensions of the same system we study. We are part of the planet's equilibrium, observers made of the same matter we measure, drawn by the same gravity that shapes the world. To measure the invisible is, in a way, to measure ourselves, to see the forces that hold us, move us, and define the very shape of our existence. The Earth is never still. It turns, it tilts, it wobbles, and it breathes through the slow movements of its oceans, air, and crust. What seems to us like a stable surface beneath our feet is, in reality, a planet in constant motion, balancing countless interactions that never stop. These motions are not random. They are the direct expression of physics, the interplay of rotation, gravity, inertia, and the distribution of mass within the planet itself. When we talk about the Earth's shape, we cannot separate it from this motion. The planet's form and its movement are two sides of the same process, each defining and sustaining the other. The most familiar of these motions is rotation, the steady turning of the planet around its axis. That motion defines the rhythm of day and night, the alternation of light and darkness that marks every hour of our lives. But rotation is only one of several intertwined motions that the Earth performs simultaneously. The planet also orbits the Sun, travelling at nearly 30 kilometers per second along an elliptical path. The Moon orbits Earth, tugging at it with a steady gravitational pull. The entire solar system moves around the centre of the Milky Way at hundreds of kilometers per second, and the galaxy itself drifts through space as part of a cluster of galaxies bound together by gravity. Every motion exists within a larger one, each with its own period, direction, and influence. Together they create a hierarchy of movement that defines not only where the Earth is, but what it is. On a smaller scale, the Earth's motion manifests as subtle variations in its rotation and orientation. The axis around which the planet spins is not fixed. It slowly shifts due to gravitational interactions with the Sun, the Moon, and even the distribution of mass within the planet. This movement, known as precession, causes the orientation of the axis to trace a slow, circular path through the sky over roughly 26,000 years. It means that the North Star is not a permanent guide. Over millennia, different stars take its place as the axis points to new positions in space. This precession changes the timing of the equinoxes and affects long-term climate cycles by altering the way sunlight falls on the Earth's surface. Superimposed on precession are smaller oscillations known as nutations, short-term wobbles caused by the varying gravitational pull of the Moon as it moves along its elliptical orbit. These wobbles slightly tilt and twist the planet's axis, introducing periodic variations in rotation that can be measured with precise instruments. Even smaller fluctuations, known as polar motion, occur as the Earth's mass shifts through processes like melting ice, ocean currents, and atmospheric changes. These shifts move the geographic poles by centimeters each year, demonstrating how closely the planet's motion is tied to the movement of its internal and external materials. Rotation itself is not perfectly constant. The length of a day changes by fractions of milliseconds due to the exchange of angular momentum between the solid Earth, its atmosphere, and its oceans. When strong winds circulate in one direction, they exert a torque that slightly accelerates, or decelerates the planet's rotation. The redistribution of water, whether through tides or seasonal changes, also modifies the moment of inertia, the measure of how mass is distributed relative to the rotation axis. Even earthquakes, by moving large masses of rock abruptly, can shift the planet's axis and alter its spin rate by imperceptible but measurable amounts. Each of these effects reflects the same principle. Motion and shape are inseparable, constantly influencing one another through gravity and inertia. The tidal interaction between Earth and the Moon is one of the most important examples of this exchange. The Moon's gravity pulls on the oceans, raising bulges of water on the side facing it and on the opposite side. These tidal bulges don't align perfectly with the Moon because the Earth rotates faster than the Moon orbits. As a result, the bulges are carried slightly ahead of the line connecting the two bodies. This misalignment exerts a gravitational torque that transfers angular momentum from Earth to the Moon. The effect slows the planet's rotation gradually and pushes the Moon slowly farther away at a rate of about 4 centimeters per year. Over time, this exchange of momentum reshapes both bodies' orbits and rotations. It's an example of how interconnected motion in the solar system truly is, how even the slow breathing of tides can alter the future of worlds. On longer timescales, the Earth's motion through space interacts with other planets, producing variations in its orbit known as Milankovitch cycles. These cycles describe periodic changes in the Earth's orbital eccentricity, axial tilt, and precession, which together influence how sunlight is distributed across the planet. Over tens and hundreds of thousands of years, these subtle variations affect climate patterns, driving the rhythm of ice ages and interglacial periods. They show that the Earth's motion is not merely mechanical, it's a driver of environmental change, a cosmic clock whose gears regulate the conditions for life. Even within the planet, motion continues at every level. The crust is divided into plates that drift atop the more fluid mantle below, moving at rates of a few centimeters per year. This slow motion reshapes the continents, opening oceans, building mountains and closing basins. It's powered by convection, the upward and downward movement of heat and material within the mantle, and maintained by the balance between heat from the core and cooling at the surface. The result is a constant recycling of the Earth's outer layer, a motion so slow that it feels like permanence but so persistent that it has remade the entire surface of the planet many times over. The core itself moves too. The outer core is a sea of molten iron and nickel swirling around the solid inner core. This flow generates electric currents that create the Earth's magnetic field. Because the flow is dynamic, the field shifts over time, drifting, reversing polarity and changing intensity. Recent studies suggest that the solid inner core might even rotate at a slightly different rate from the rest of the planet, occasionally speeding up or slowing down relative to the mantle. This differential motion affects the magnetic field and contributes to the planet's internal energy balance. Deep below our feet, motion continues in silence, shaping the conditions on the surface above. On the scale of human experience, these motions are invisible. The Earth feels still beneath us because we move with it. Every step, every breath, every heartbeat happens within this continuous motion, synchronized with it. But we can detect its effects through careful observation. The Coriolis effect, for example, arises because of rotation. It causes moving air and water to curve rather than travel in straight lines, shaping global wind patterns and ocean currents. Storms rotate in opposite directions in the northern and southern hemispheres because of this same effect. Even the path of an airplane or a missile must account for the planet's rotation, or it will miss its target. The invisible motion of the Earth defines the framework of motion for everything upon it. The motion of the planet also defines how we perceive time. The rotation of the Earth around its axis determines the length of a day, while its orbit around the Sun defines the year. Yet these cycles are not perfectly constant. Leap seconds are occasionally added to atomic clocks to synchronize them with the slowing rotation of the planet. The very passage of time, as we define it, depends on the Earth's motion through space. Without that motion, time would lose its natural rhythm. Without measurement, we would never know that rhythm changes. Each of these motions, from the rotation of the core to the orbit around the Sun, is governed by conservation laws, the unbreakable principles of physics that ensure balance. Angular momentum once set must be conserved unless acted upon by an external torque. Energy, once distributed, must transform but cannot vanish. These laws mean that the Earth's motions are linked not just to their causes but to each other. When mass moves from the poles to the equator, the planet's rotation adjusts. When the Moon pulls on the oceans, the spin of the Earth slows. When the mantle convects, the surface drifts. Every motion echoes through the whole system, binding it together in a web of balance. It's easy to think of this constant activity as chaotic, but it is profoundly ordered. The interactions follow precise mathematical relationships, described by Newton's laws of motion and gravitation, refined by Einstein's theory of general relativity. The curvature of space-time created by the Earth's mass governs its orbit, just as the planet's internal energy drives its geologic cycles. Motion and shape are consequences of the same physical principles expressed at different scales. When the Earth moves, it does so not randomly but according to patterns that can be predicted, measured and understood. Even the atmosphere, which seems fluid and unpredictable, follows the same laws. Air moves because of pressure differences, which arise from uneven heating by the Sun. The rotation of the planet modifies these flows, organising them into stable circulation patterns like the trade winds and jet streams. These patterns, in turn, affect how heat and moisture are distributed across the planet. The oceans respond in kind, circulating slowly but powerfully, transferring heat from equator to pole and shaping climates. The combined effect of these motions keeps the planet's surface temperature within a range that supports life. Without them, the world would swing between extremes of heat and cold. The Earth's motion doesn't just define its shape, it regulates its habitability. At the most fundamental level, the Earth's motion is a manifestation of the universe's initial conditions. When the solar system formed from a rotating cloud of gas and dust, the conservation of angular momentum ensured that every planet would spin. The direction and speed of that spin depended on the details of the collisions and accretions that built each world. The Earth's rotation, its axial tilt, and even its orbital inclination are remnants of that early history, preserved across billions of years. What we experience as sunrise and sunset, as seasons and tides, are echoes of the cosmic motion that began before the planet itself existed. And yet, even as the Earth moves through space, it maintains balance. The centrifugal effect of rotation counteracts gravity just enough to produce the equatorial bulge. The orbit around the Sun balances gravitational attraction with inertial motion, creating a stable path that has endured for eons. The Moon's orbit stabilizes the tilt of the planet, preventing chaotic variations that could disrupt climate and ecosystems. Every motion is part of a larger equilibrium, a dynamic balance that persists not because of stillness, but because of continuous adjustment. When we consider all these motions together, rotation, revolution, precession, nutation, plate drift, convection, and orbital travel, the planet becomes more than a physical object. It becomes a dynamic system of energy and balance, moving through space with perfect precision. Every motion affects the others, yet none of them overwhelms the whole. The result is stability through motion, order through change. The Earth does not remain constant despite its movement, it remains constant because of it. From our limited perspective, these processes unfold slowly, almost imperceptibly. A day passes, a season changes, a tide rises and falls, and it feels as though the world remains the same. But across the deep timeline of the planet, each of these motions accumulates. The rotation slows, the orbit shifts, the continents drift, and the planet's axis traces its slow circle through space. Over millions of years, these subtle changes reshape the entire surface, rearrange the pattern of climate, and alter the very conditions of life. The Earth in motion is not simply a planet moving through space, it is a planet evolving through time. The beauty of this motion lies in its invisibility. We live within it, carried along by it, unaware of its speed or scale. The ground beneath us turns at hundreds of meters per second, yet we feel nothing. The planet races around the sun at 30 kilometers per second, yet the sky above feels still. The entire solar system moves through the galaxy, yet the stars seem fixed. The absence of sensation does not mean absence of motion. It means that motion is absolute. Everything moves together, in balance, with no fixed reference to measure against. The universe itself is a fabric of motion, and the Earth is one thread woven into it. Every measurement we make, every observation of the planet's shape and balance, is an attempt to trace that motion. The path of satellites, the tilt of gyroscopes, the flow of oceans, the shifting of tectonic plates. All of these are ways to map the unseen dynamics that define the Earth's existence. To understand the planet's motion is to understand its stability, its capacity to sustain life, and its place within the wider cosmos. And so the Earth continues, turning quietly, orbiting steadily, shifting subtly beneath its oceans and skies. The motions intertwine in perfect coordination, shaping everything from the length of a day to the height of a tide. The planet's shape, its gravity, and its motion are not separate phenomena but parts of one continuous reality. A reality where balance arises not from stillness, but from perpetual movement. And as it keeps turning, orbiting and shifting, the next question unfolds naturally. How does all this motion, this continuous interplay of energy and gravity, sustain the balance of the planet's form deep within, the hidden equilibrium of density, pressure and heat that holds the world together from its molten heart to its curving surface? When we speak of the shape of the Earth, we think of matter, rock, water, air, the tangible elements that give form to our world. But beyond the limits of physical substance, there is another kind of shape, one that can't be touched or seen, but which defines everything that matter can do. It is the shape of space itself, the quiet geometry that underlies gravity, motion, and time. To understand how the Earth truly exists, not just as an object but as a presence in the fabric of the universe, we must leave the surface behind and step into the framework described by Einstein's theory of general relativity. There, the planet is no longer simply a sphere in empty space, but a region where space and time are curved together by mass. The Earth does not merely sit in space, it shapes space, bends it, and moves through the geometry it creates. This idea was revolutionary when Einstein introduced it in 1915. For centuries, gravity had been understood as a force acting at a distance, pulling objects toward one another through invisible attraction. Newton described it as a universal law, simple and elegant. Every particle of matter pulls on every other particle in proportion to their masses and inversely to the square of the distance between them. It explained the falling of apples and the motion of planets with astonishing precision. Yet it left one question unanswered. How could that force act across the emptiness of space, instantly and without a medium? Einstein replaced that mystery with a new vision. He proposed that space and time were not separate entities, but parts of a single, four-dimensional continuum, space-time, and that mass and energy could curve this continuum, creating what we perceive as gravity. In this view, the Earth does not pull objects toward it in the Newtonian sense. Instead, its mass distorts the geometry of space-time around it, and objects follow the natural paths within that curved geometry. Those paths are called geodesics, the straightest possible lines in curved space. To us, they appear as curved trajectories, but to the objects themselves, they are lines of least resistance, the natural flow of motion. A falling apple doesn't feel a force pulling it downward. It's simply moving along a path that space-time defines. Likewise, the Moon doesn't orbit the Earth because it's being pulled around. It moves freely through the curved space created by Earth's mass, tracing an ellipse because that's the geometry of its environment. The shape of this curvature is subtle yet profound. Near the surface of the Earth, the distortion of space-time is mild compared to that around massive stars or black holes, but it is enough to define everything we experience as gravity. Space is not flat here. It curves gently inward, wrapping around the planet like a soft indentation in a cosmic fabric. Time, too, is affected. The flow of time runs slightly slower in stronger gravitational fields, meaning that clocks on the surface of the Earth tick more slowly than clocks in orbit. The difference is minuscule, only a few billionths of a second per second, but it's measurable, and it matters. The satellites that make up the global positioning system must account for this difference. Their onboard clocks are adjusted to compensate for both gravitational time dilation and the effects of their motion. Without these relativistic corrections, GPS positions would drift by kilometers each day. What this tells us is that the shape of the Earth is inseparable from the shape of space-time around it. The geoid, the surface of equal gravitational potential, is not just a physical boundary of mass but a contour within curved space. The curvature created by the Earth's mass defines how gravity acts, how time flows, and even how light travels near the planet. When light passes through this curved region, its path bends slightly, just as starlight bends around the sun. This bending, though tiny for the Earth, has been confirmed by sensitive experiments using radar signals sent between satellites. The results match Einstein's predictions precisely. The mathematics of this curvature are expressed through Einstein's field equations, a set of relationships that tie together the geometry of space-time with the distribution of mass and energy. The equations are complex, but their essence can be summarized simply. Matter tells space-time how to curve, and space-time tells matter how to move. This reciprocity is what makes the theory so powerful. It doesn't treat gravity as an external force, but as a property of space itself. The Earth's presence modifies the structure of space-time, and that structure dictates the behavior of everything around it, from falling raindrops to orbiting satellites. To visualize this, imagine a stretched sheet representing flat space-time. If you place a heavy object like a metal ball on the sheet, it will sink slightly, creating a depression. A smaller ball placed nearby will roll toward it, not because of a force acting at a distance, but because the sheet's surface is now curved. The smaller ball follows the geometry of the sheet. This image is a two-dimensional analogy of the Earth's effect on space-time. In reality, the curvature occurs in 4 dimensions, involving both space and time, but the principle is the same. The Earth sits in space-time, bending it just enough that everything nearby moves in response to that curvature. The curvature extends far beyond the surface. Its influence gradually weakens with distance, but never fully disappears. Even the orbit of the Moon, nearly 400,000 kilometers away, is guided by this geometry. The International Space Station, circling the Earth at an altitude of about 400 kilometers, is in free fall within this curved space. It remains in orbit because its forward velocity continually carries it around the planet, matching the curvature of space-time. Astronauts inside the station experience weightlessness not because gravity is absent, but because they are following the same curved path as the station itself. In relativity, free fall is the natural state of motion, the straightest possible path through curved space-time. This understanding changes how we think about shape. The Earth's form is not just the outline of its surface, but the imprint it leaves on the geometry of the universe. Its mass, rotation, and internal density all contribute to the specific way space-time bends around it. Even the planet's spin affects the curvature slightly, producing a phenomenon called frame dragging. When a massive object rotates, it drags space-time along with it, twisting the surrounding geometry. This effect, predicted by Einstein and confirmed by the gravity probe B experiment in 2011, means that the space near the Earth's poles is literally being pulled around by the planet's rotation. The experiment measured the orientation of ultra-sensitive gyroscopes in orbit, detecting tiny changes in their axes caused by the twisting of space-time. Though the effect is extremely small, less than 2 arcseconds per year, it is real and measurable. It shows that the Earth doesn't just curve space, it stirs it. Frame dragging has consequences beyond theoretical interest. It affects the orbits of satellites, the precession of gyroscopes, and even the behaviour of light near the rotating planet. It's a reminder that the boundary between space and matter is not rigid. The planet's movement influences the geometry around it, and that geometry, in turn, influences everything that moves through it. The Earth is not an isolated object in space. It is part of a dynamic interaction between mass and space-time, constantly shaping and being shaped by the environment it inhabits. The concept of curved space also explains why gravity can appear both universal and local. On the scale of the Earth, gravity pulls everything toward the centre, defining the direction we call down. On the scale of the solar system, that same gravity merges with the sun's, creating a combined field that governs the orbits of planets. On larger scales, the curvature of space-time produced by entire galaxies shapes the motion of stars and the bending of light across cosmic distances. The same principle applies everywhere, from the smallest mass to the largest cluster of galaxies. What changes is only the strength and scale of the curvature. Near the Earth, the curvature is gentle, but measurable in precise ways. Time dilation provides one example. Gravitational redshift offers another. Like climbing out of the planet's gravitational field loses a tiny amount of energy, causing its wavelength to stretch slightly toward the red end of the spectrum. This effect, predicted by relativity, has been confirmed by experiments comparing atomic clocks at different altitudes. A clock on a mountaintop runs slightly faster than one at sea level, because time flows more quickly in weaker gravitational fields. Though the difference is measured in billionths of a second, it's essential for technologies that rely on timing accuracy. In this sense, the flow of time itself is part of the Earth's shape, another dimension of the curvature that defines its gravitational identity. From a relativistic perspective, even the familiar concept of the geoid gains a deeper meaning. The geoid represents a surface of equal gravitational potential in the Newtonian sense, but in relativity, that potential corresponds to constant time dilation. In other words, the geoid can also be seen as a surface where clocks would tick at the same rate. The geometry of space and the flow of time are inseparable. Flattening, bulging, and variations in density are not just physical irregularities, but distortions in space-time itself. The Earth's true shape, therefore, is not confined to 3 dimensions. It extends into the 4th dimension of time. This insight connects the physics of the planet to the structure of the cosmos. The same curvature that holds us to the ground links us to the gravitational field of the Sun, the galaxy, and ultimately the universe. Space is not an empty backdrop in which the Earth exists. It is the very fabric that gives the planet its location, orientation, and motion. To understand the shape of the Earth is to understand how the universe accommodates it, how mass bends the geometry of space, and how that geometry governs motion and time. The curvature around the Earth is small enough that everyday life proceeds as though space were flat. Newton's equations work perfectly well for almost all practical purposes. Yet, at the edges of precision, in the timing of satellites, the synchronization of clocks, and the trajectories of spacecraft, the curvature reveals itself. Engineers and physicists account for it routinely, embedding relativity into the operation of global systems. The invisible warping of space-time has become part of the infrastructure of modern civilization, guiding signals, navigation, and communication across the planet. The Earth's interaction with space-time also reveals how finely balanced its motion is. The planet's mass curves space just enough to bind the Moon in orbit without pulling it down. Its rotation twists space-time enough to create measurable effects without destabilizing its field. Its orbit around the Sun follows the exact curvature required for stability over billions of years. These balances are not coincidences. They are the natural outcomes of the laws of relativity, which ensure that mass, energy, and geometry maintain harmony through motion. It's striking to realize that the very experience of standing on the ground is an interaction with curved space. What we feel as weight is the result of the ground pushing upward against us, preventing us from following the straight path that space-time dictates. If the Earth was suddenly to vanish, we wouldn't be pulled downward. We would continue in the direction we were already moving, following the curve that space provides. Gravity, in this sense, is not a pull, but a constraint, the result of space curving around mass and forcing everything within it to follow that curvature. The shape of space around the Earth also interacts with energy. Electromagnetic waves, including light, radio, and heat, travel along the curved paths of space-time. This means that even the transmission of information is shaped by the Earth's gravity. Light from distant stars bends slightly as it passes near the planet, and radio signals from spacecraft must be corrected for the time delay caused by the curvature they traverse. Every communication that crosses the heavens, every photon that touches our instruments, carries within it the imprint of the Earth's gravitational field. These effects, though small, connect the human scale to the cosmic scale. They show that relativity is not an abstraction, but a description of the real geometry in which we live. The same principles that explain the bending of starlight around the Sun also explain why a clock on a satellite must be adjusted by nanoseconds. The universe operates on a single coherent framework, and the Earth is one example within it, a curved region of space and time, stable, spinning, and alive. When we describe the Earth as round, we describe only the beginning of its shape. Beneath the physical roundness lies the curvature of space-time, invisible yet universal, defining how everything moves, how time flows, and how gravity connects us to the rest of the cosmos. The planet's mass sculpts space into a gentle well, its rotation twists that well slightly, and within that structure, every motion, from a falling leaf to an orbiting satellite, finds its path. The true shape of the Earth, seen through the lens of relativity, is not a surface at all, but a field of curvature, a seamless blending of space and time moulded by the weight of a world. Surrounding the solid Earth and its oceans is a layer so thin and delicate that, from space, it looks almost like a soft glow, a faint blue halo clinging to the planet's curve. That halo is the atmosphere, the gaseous envelope that both defines and protects life on Earth. Though it seems weightless and transparent, it is a massive dynamic part of the planet's physical system. It shapes the world's temperature, regulates its climate, and interacts constantly with the solid and liquid layers below. And though it extends only a few hundred kilometers outward, it participates in the same gravitational and rotational balance that determines the planet's shape. The atmosphere is not simply attached to the Earth, it is part of its structure, a mobile, responsive extension of the planet's mass and motion. From the surface, the atmosphere feels infinite. We breathe without thinking, we watch clouds drift, we see light scatter through air so vast it appears boundless. But measured against the planet itself, it is remarkably thin. Most of the mass of the atmosphere lies within the first 10 kilometers above the ground, less than 1/2000th of the Earth's radius. By 100 kilometers, where space officially begins, the air is so rarefied that a single cubic meter contains fewer molecules than a breath at sea level. And yet, this thin shell of gases exerts weight. Every square meter of the surface supports a column of air weighing about 10 metric tons. That weight, distributed evenly across the planet, presses inward with what we call atmospheric pressure, the force that balances the outward flow of gases into space and keeps the atmosphere in place. Gravity holds the atmosphere close, Each molecule of air is pulled toward the centre of the planet, but the random motion of those molecules, or their temperature, gives them energy that resists complete compression. The result is an exponential decrease in density with altitude. Air is thick near the surface and thins rapidly upward. This gradient arises naturally from physics. The balance between thermal motion and gravity defines what scientists call the scale height, the distance over which atmospheric pressure decreases by a factor of e, the base of natural logarithms. On Earth, that distance is about 8.5 kilometers. It's the mathematical signature of how the atmosphere's mass is distributed, not evenly, but tightly bound by gravity's continuous pull. This balance is dynamic, not static. The temperature of the atmosphere varies with height, and those variations influence how gases mix and move. In the lowest layer, the troposphere, temperature generally decreases with altitude, creating the conditions that drive weather. Convection dominates here. Warm air rises, cools, and sinks again, forming the turbulent cycles that produce clouds, winds, and storms. Above the troposphere lies the stratosphere, where temperature increases with height due to the absorption of ultraviolet radiation by ozone. This reversal of the gradient suppresses convection, creating a more stable layer where air moves slowly and predictably. Higher still, in the mesosphere and thermosphere, temperatures fluctuate dramatically as energy from the sun interacts with thinner gases. Even higher, in the exosphere, molecules move freely, colliding rarely, some escaping altogether into space. These layers, though named separately, are not rigid boundaries but transitions in energy and density. Together they form a continuous gradient of gas, stretching from the surface to hundreds of kilometers above. The atmosphere's shape mirrors that of the Earth beneath, slightly flattened at the poles and extended at the equator due to rotation. Centrifugal force acts on the air just as it acts on the solid planet, reducing effective gravity slightly at lower latitudes. This effect, though subtle, causes the atmosphere to bulge outward along the equatorial belt, forming a faintly oblate shell. The same balance of rotation and gravity that shapes the Earth's solid surface also sculpts the invisible air around it. Rotation does more than alter shape, it organizes motion. The Earth spinning causes the Coriolis effect, which deflects moving air to the right in the northern hemisphere and to the left in the southern. This deflection shapes global circulation patterns. Warm air rises at the equator, flows toward the poles, and sinks in subtropical regions, forming vast cells of convection. These cells create trade winds, westerlies, and polar easterlies, the great belts of motion that encircle the globe. The atmosphere thus becomes a rotating fluid, its motion synchronized with the planet's spin yet constantly rearranged by temperature and pressure gradients. From space, this movement appears as swirls and streams of clouds, but in physics, it's the manifestation of angular momentum conserved within a rotating sphere. The atmosphere's interaction with light gives it its visible halo. Sunlight, composed of all wavelengths, scatters when it meets air molecules. Shorter wavelengths, blues and violets, scatter more efficiently than longer reds, making the sky appear blue during the day. At sunrise and sunset, when sunlight passes through more air, the blue light scatters away, leaving reds and oranges to dominate. This scattering, known as Rayleigh scattering, reveals that the halo we see is not an illusion, but a real optical consequence of the atmosphere's composition and thickness. It's the physical trace of countless collisions between light and air, an optical fingerprint of the layer that shields and sustains life. From an orbital perspective, that halo is more than beautiful. It's a precise indicator of the planet's curvature and the extent of its gravitational field. Astronauts describe seeing a razor-thin line of blue along the horizon, fading quickly into blackness. That narrowness shows just how confined the atmosphere is by gravity. It also illustrates how fragile it is, a tenuous layer standing between the surface and the void. Within that layer, all weather, all wind, all breath, and all sound occur. Every living thing on the surface depends on it, yet it is, in cosmic terms, as thin as the skin of a soap bubble. Despite its delicacy, the atmosphere participates in the planet's mass balance. It adds weight, about 5 quadrillion tons, to the total mass of the Earth. This additional mass slightly alters the planet's moment of inertia and contributes minutely to its gravitational field. The shape of the geoid, when measured precisely, includes the influence of the atmosphere. Though its effect is small compared to rock or water, it is measurable. Variations in air pressure redistribute this mass continually, changing the Earth's gravitational field by tiny but detectable amounts. Satellites like GRACE, designed to measure such variations, can sense seasonal shifts in atmospheric pressure as the planet's winds and temperatures evolve. The atmosphere also interacts with the planet's rotation. Because it moves, it exchanges angular momentum with the solid Earth. When strong winds develop, such as during large-scale weather systems, they can slightly alter the rotation rate of the planet. A powerful jet stream or monsoon system can change the length of a day by microseconds. When the circulation weakens, the planet's spin returns to its prior state. These exchanges occur continuously, demonstrating that the air above is not separate from the planet below, but part of the same rotating system. The solid Earth, the oceans, and the atmosphere share angular momentum, maintaining overall balance even as energy flows among them. The atmosphere's shape is further influenced by heating from the sun. Because the planet is tilted on its axis, solar energy is distributed unevenly, with more heat reaching the equator than the poles. This difference drives large-scale circulation, but it also alters the vertical structure of the atmosphere. Warmer air expands, causing the atmospheric column to rise higher in equatorial regions. Cooler air at the poles contracts, lowering the height of pressure surfaces. The result is a subtle distortion. The atmosphere is thicker over the tropics and thinner over the poles, adding another layer to the planet's oblate symmetry. Even in the realm of gas, geometry follows the same physics. Energy, mass, and rotation find equilibrium in shape. Higher up, the interaction between the atmosphere and space becomes more direct. In the thermosphere and exosphere, solar radiation ionizes atoms and molecules, creating charged particles that respond to magnetic fields. These particles form the ionosphere, a region crucial for radio communication and satellite operation. It reflects and refracts electromagnetic waves, allowing long-distance signals to travel beyond the horizon. The ionosphere also glows faintly when charged particles from the solar wind collide with atoms in the upper atmosphere, producing the auroras, moving curtains of green, red and violet light that trace the planet's magnetic field lines near the poles. This shimmering edge of the halo is both a scientific and natural phenomenon, the visible evidence of energy exchange between the Earth and the Sun through the medium of the atmosphere. The atmosphere extends farther than most people realize. Even at altitudes of several hundred kilometers, traces of it remain. The boundary where it merges with space is not sharp but diffuse. Molecules escape gradually, carried away by thermal energy or the solar wind. Some atoms of hydrogen and helium drift off into interplanetary space, while heavier gases remain bound by gravity. The rate of loss is balanced by replenishment from volcanic outgassing, chemical reactions and biological processes. Over geological time, this balance has maintained the atmosphere's composition within narrow limits, allowing life to flourish. The atmosphere's endurance is a product of both gravity and motion, the constant interplay that keeps it stable while allowing it to evolve. What gives the atmosphere its unique shape is not only gravity but temperature. As gases heat, they expand. As they cool, they contract. This expansion and contraction change the height of pressure levels, effectively reshaping the atmosphere from day to day. The tropopause, the boundary between the troposphere and the stratosphere, rises and falls with temperature variations. Even the thermosphere, hundreds of kilometers above, swells and shrinks with the solar cycle. During periods of intense solar activity, it can expand enough to increase drag on satellites in low Earth orbit, shortening their lifetimes. In quiet periods, it contracts, reducing drag but altering how energy from the sun interacts with the planet. The atmosphere's outer boundary breathes with the rhythm of solar radiation, a cosmic pulse woven into the Earth's own motions. The shape of this halo is, therefore, a living boundary, a flexible, responsive interface between the solid planet and the vacuum beyond. It reflects every process that happens below: volcanic eruptions that inject particles into the stratosphere, forest fires that spread aerosols through the troposphere, ocean currents that release moisture and heat. Each event leaves a signature in the distribution of gases, temperatures, and pressures. The atmosphere records the history of the Earth's surface as surely as rock layers record its geological past. Even the smallest variations in composition affect its optical and thermal properties, altering how light and heat move through it. These feedbacks connect climate, chemistry, and geometry into a single interdependent system. At the molecular level, the atmosphere's structure is governed by statistical physics. Each molecule moves independently, colliding, exchanging energy, and scattering light. But when taken together, these countless collisions produce macroscopic patterns, pressure gradients, temperature profiles, and winds. The same randomness that defines molecular motion gives rise to the ordered patterns we recognize as weather. And through those patterns, the shape of the atmosphere evolves moment by moment, always changing yet maintaining overall equilibrium. In this way, the atmosphere acts as both a physical structure and an active participant in the Earth's balance. It smooths temperature differences between day and night, redistributes energy from equator to pole, and protects the surface from harmful radiation. Its composition, primarily nitrogen and oxygen with traces of argon, carbon dioxide, and other gases, results from billions of years of interaction between life and the planet. The presence of oxygen, for example, is entirely biological in origin, produced by photosynthesis. Without life, the atmosphere would look completely different. Thinner, more inert, more like that of Mars or Venus. Its current state reflects the planet's evolution as much as its geology does. The atmosphere's motion also affects the perception of shape from space. The outer edge of the halo, what astronauts see as a delicate glow, defines the visible boundary between Earth and the cosmos. But that boundary shifts with time, expanding during the day as the upper layers heat, contracting at night as they cool. The planet's visible radius changes by small but measurable amounts. From orbit, instruments can detect these changes and correlate them with temperature, solar flux, and composition. The shape of the Earth, when seen as a combination of solid, liquid, and gas, is not fixed. It oscillates continuously in response to both internal and external energy. The physics governing the atmosphere's shape mirrors the equations that govern the rest of the planet. Hydrostatic equilibrium, the balance between gravitational pull and pressure gradient, holds in both rock and air. In the crust, that balance is static and solid. In the atmosphere, it's dynamic and fluid. The same principles that determine the flattening of the Earth determine the vertical profile of air pressure. Gravity pulls inward, motion pushes outward, and equilibrium defines the structure. The difference lies only in the timescale and medium. The atmosphere adjusts in hours or days, the solid Earth adjusts over millennia. Yet both express the same balance between force and resistance that defines the shape of the world. Seen from space, that hidden halo represents more than air. It is a visible sign of balance, the outer expression of the planet's gravity, motion, and energy. Its faint blue line marks the limit of where the Earth's shape gives way to space, a reminder that even the air we breathe is part of the planet's geometry. It curves with the planet, moves with its rotation, and shifts with its heat. It is, in every sense, an extension of the world's physical form, transparent, transient, and vital. The Earth is not a perfectly steady spinner. It turns with consistency enough to define time itself, yet hidden within that regular motion are subtle variations, small tilts, shifts, and oscillations that cause the planet to wobble as it rotates. These wobbles are not flaws in its movement, but natural outcomes of its structure, its internal distribution of mass, and the gravitational influences acting upon it. When scientists say the Earth wobbles, they mean that its rotation axis, the imaginary line running from pole to pole, moves slowly in space and even within the planet itself. The result is a motion both elegant and intricate, one that connects the deep interior of the Earth to its atmosphere, oceans, and even the distant moon. To picture this, imagine a spinning top. When it rotates rapidly, it seems stable, its axis standing upright. But as friction slows it down, the top begins to precess. Its axis starts tracing a circle in the air. The same thing happens to the Earth, though on a much longer time scale. The planet's axis traces a slow circle through the sky, taking about 26,000 years to complete one rotation. This long-term motion is called axial precession, and it arises because the Earth is not a perfect sphere. Its equatorial bulge, the result of its rotation, gives the Sun and Moon something to pull on. Their gravitational attraction on that bulge exerts a torque, causing the axis to shift orientation gradually, just like the tops. This precession changes the coordinates of the heavens. Over millennia, the position of the North Star changes, and the timing of the seasons slowly drifts relative to the calendar. It's why, in ancient times, different stars marked the celestial pole, and why in the far future others will take their place. This cycle, imperceptible on human timescales, has profound implications for climate. The precession alters the timing of when Earth's hemispheres tilt toward or away from the Sun during its elliptical orbit, influencing the distribution of solar energy and contributing to the pattern of ice ages over tens of thousands of years. It is one of the key components of the Milankovitch cycles, the rhythmic variations in Earth's motion that modulate its climate. But the story of the Earth's wobble doesn't end with precession. Superimposed upon that slow movement are smaller oscillations known as nutations. These are periodic wobbles caused by the gravitational interactions between the Earth, Moon, and Sun. The most significant of these occurs over an 18.5-year cycle, corresponding to the regression of the Moon's orbital nodes. As the plane of the Moon's orbit tilts and rotates relative to the Earth's equator, it changes the direction and magnitude of the gravitational torque on the planet's equatorial bulge. The result is a small but measurable oscillation in the tilt of the Earth's axis. Only a few arc-seconds, yet enough to influence the position of the celestial poles and the apparent motion of the stars. This dance between precession and nutation creates a complex pattern of motion, but it remains predictable because it follows the laws of angular momentum and gravitational dynamics. The planet's total angular momentum must remain constant unless acted upon by an external torque. So when external forces vary, the orientation of the axis adjusts to preserve that balance. The wobble, therefore, is not instability, it is equilibrium in motion, a continuous response to the shifting gravitational environment. Another form of wobble, smaller still, occurs within the Earth itself. It's called polar motion, the wandering of the rotation axis relative to the surface of the planet. Unlike precession or nutation, which describe how the axis moves in space, polar motion describes how it moves within the Earth's crust. The geographic poles are not fixed points. They drift by several centimetres to metres each year. This motion is caused by changes in the distribution of mass within the planet. Movements of water, air, ice, and even molten rock deep below. When large ice sheets melt, when groundwater is depleted, or when vast ocean currents shift, the balance of mass changes, and the axis adjusts accordingly. This adjustment is governed by the conservation of angular momentum. When mass moves closer to or farther from the rotation axis, the planet compensates by changing its orientation slightly, just as a figure skater does when drawing in or extending their arms. This analogy captures the essence of the Earth's behaviour. To maintain balance, it must wobble. The phenomenon was first detected in the late 19th century by astronomer Seth Carlo Chandler, who observed a periodic oscillation of the poles with a period of about 433 days. This motion, now known as the Chandler wobble, represents the free oscillation of the planet's rotation axis relative to its crust. It's caused by the Earth's elastic response to shifting loads and internal forces, and its amplitude is typically a few meters at the surface. The Chandler wobble interacts with another, longer-term variation called the annual wobble, which results from seasonal redistributions of mass, the movement of water and air as seasons change. When these two oscillations combine, they create complex patterns of polar motion, sometimes amplifying each other, sometimes cancelling out. The precise behaviour of the wobble varies from year to year, influenced by phenomena such as El Niño, monsoon cycles, and the melting or accumulation of polar ice. Satellites equipped with laser ranging systems can now track these movements to within millimeters, providing real-time data on how the Earth's rotation responds to its changing mass distribution. The wobbles are not limited to surface or atmospheric effects. Deep within the Earth, motion continues in the fluid outer core, where molten metal circulates and drives the planet's magnetic field. These flows alter the distribution of density and can subtly influence rotation. Seismic studies and magnetic observations suggest that the inner core may rotate at a slightly different rate than the mantle, leading to internal torques that affect the planet's overall angular momentum. When the rotation of the core changes, even by a small amount, the solid Earth adjusts and the wobble responds. The result is a system where every layer, from the atmosphere to the core, participates in maintaining balance. On geological timescales, the orientation of the Earth's axis has varied dramatically. Evidence from sediments, fossils, and magnetic records shows that the tilt, known as obliquity, oscillates between about 22 and 24.5 degrees over a cycle of roughly 41,000 years. These changes in obliquity alter the contrast between seasons, strengthening or weakening them depending on the tilt. When the tilt is greater, seasonal extremes are more pronounced. When it's smaller, climates become milder. Combined with precession and changes in orbital eccentricity, these cycles create the rhythmic patterns of glacial and interglacial periods recorded in the planet's history. The wobbling Earth, therefore, is not just a mechanical system. It is a climate engine, shaping the rhythm of ice and warmth that governs the biosphere. These motions also affect the length of a day. The redistribution of mass, both at the surface and within, changes the planet's moment of inertia. When water moves from high latitudes toward the equator, as during ice melt, the moment of inertia increases and the rotation slows slightly. Conversely, when mass moves toward the poles, the planet spins faster. The differences are tiny, milliseconds per day, but measurable with atomic clocks. Earthquakes, volcanic eruptions, and even large weather systems can cause brief, localized adjustments to the rotation rate. These fluctuations demonstrate how sensitive the Earth is to internal and external influences, and how its motion continually adjusts to maintain equilibrium. The physics behind these phenomena can be described through rigid body dynamics and the equations of angular momentum. The Earth, however, is not perfectly rigid. Its elasticity allows it to deform under stress, and its fluid components, oceans and atmosphere, redistribute mass constantly. This combination makes its rotation complex but beautifully consistent. The equations that govern it include terms for inertia, tensors, external torques, and damping effects, all interacting to produce the observed wobbles. When modelled accurately, these equations reproduce the behaviour measured by satellites and astronomical observations. What might seem chaotic, the wandering of the poles, the oscillation of the axis, the shifting of rotation, emerges as a coherent system following precise physical laws. The wobble is also influenced by the gravitational pull of the Moon. Tidal forces continually deform the Earth, raising bulges in both the oceans and the crust. These tidal deformations move around the planet as it rotates, transferring angular momentum between Earth and Moon. The process gradually slows the planet's spin and pushes the Moon farther away. The rate of slowing is about 2 milliseconds per century, imperceptible day to day but cumulative over time. Hundreds of millions of years ago, days were shorter, and there were more of them in a year. Fossil corals and tidal sediments record this rhythm, showing how the Earth's wobble and spin have evolved together across epochs. When viewed in full, the Earth's wobble is not a single motion, but a superposition of many: precession, nutation, Chandler wobble, polar motion, tidal deformation, and rotational drift, all operating on different timescales and amplitudes. Each component tells part of the story of how the planet maintains its balance amid constant change. The axis moves because gravity, inertia, and mass distribution are never perfectly symmetrical, and because the Earth is a living system, always shifting. The stability we experience, the reliable cycle of days and nights, seasons and years, arises from this dynamic equilibrium. The wobble doesn't threaten the planet's balance, it sustains it. The observation of the wobble has become one of the most precise achievements in Earth science. Using techniques such as very long baseline interferometry, VLBI, scientists can measure the orientation of the planet's rotation axis relative to distant quasars with millimeter precision. Laser ranging to satellites and the Moon provides additional data, allowing the reconstruction of the Earth's rotation over decades. These measurements confirm that the planet's spin, though complex, remains extraordinarily stable. The variations, though small, encode information about the redistribution of mass, the elasticity of the crust, the flow of the core, and the behaviour of the oceans and atmosphere. The wobble, in other words, is a record of everything the planet does. From a broader perspective, the Earth's wobble places it within the same class of rotating bodies as other planets and stars. Mars wobbles more than Earth, because it lacks a large moon to stabilise its tilt, leading to more extreme climate variations. Jupiter's massive size and fast rotation give it a smaller relative wobble, while Saturn's moons keep its axis remarkably steady. Even the Sun wobbles slightly as its planets tug on it, causing the star to move in tiny loops around the solar system's centre of mass. The same physics applies everywhere. Angular momentum conserved, mass redistributed, equilibrium achieved through motion. On human timescales, these wobbles are invisible, their cycles far longer than lifetimes. Yet their consequences shape the world we inherit. The stability of seasons, the pacing of ice ages, the subtle drifts in day length that atomic clocks now track with precision. The wobbling Earth is both dynamic and dependable, its motion both complex and predictable. It demonstrates that stability in nature is never static. It's the result of constant, balanced movement. When we think of the Earth as wobbling, it's easy to imagine fragility, but the truth is the opposite. The wobble is evidence of the planet's resilience. It shows that the Earth can flex, shift, and adjust without losing its coherence. Its rotation axis wanders, but it never strays far. Its motion fluctuates, but it never collapses. The planet's balance endures because it's not rigid, it's responsive. The Earth does not exist in isolation. It is one among billions of worlds, each shaped by the same physical laws but expressed through different conditions: mass, temperature, composition, distance from their stars, speed of rotation, and histories written in collisions and accretion. To understand what makes our planet shape what it is, it helps to step beyond it for a moment, to see it as one example among many. When we compare the Earth to its planetary neighbours, to moons, asteroids, and gas giants, we begin to see that roundness, flattening, and irregularity are not arbitrary traits, but consequences of physics played out across the cosmos. Every large body in space tends toward a round shape. That tendency comes from gravity, which pulls matter inward equally from all directions. When an object grows massive enough, its gravity overcomes the strength of its material, forcing it into hydrostatic equilibrium, the condition where inward gravitational pull is balanced by the outward pressure of its own matter. The result is a sphere, or nearly so. This principle explains why planets, stars, and large moons are round, while small asteroids and comets are irregular. The difference is scale. A rock a few kilometers wide can resist gravity's pull because its internal strength, the chemical bonds between its atoms, can hold its shape. But as an object grows larger, its own weight overwhelms that strength and it collapses into roundness. Earth's roundness, therefore, is not unique. It's the natural outcome of its size and gravity. But the exact details of that shape, the slight flattening at the poles, the equatorial bulge, the uneven distribution of mass, arise from rotation and composition. These same influences operate on every other world, producing a spectrum of forms that reveal the balance between gravity, motion, and material strength. Take Jupiter, for instance, the largest planet in the solar system. It rotates once every 10 hours, far faster than Earth, and its rapid spin causes an enormous equatorial bulge. Its diameter at the equator is more than 10,000 kilometers greater than its diameter from pole to pole. Jupiter's shape is an exaggerated version of the Earth's, an oblate spheroid stretched by centrifugal force. Because Jupiter is made mostly of gas, it deforms easily under rotation, and the result is a planet visibly flattened, its stripes curving around like rings of a spinning disk. Saturn, spinning almost as fast and composed largely of lighter gases, shows an even greater flattening. Viewed from a distance, its poles are noticeably compressed, its equator swollen outward. These planets illustrate the limit of how far rotation can distort a world before gravity reasserts control. Compared to them, Earth's flattening is modest, about 1 part in 300. Its rotation period of 24 hours is slow enough, and its material rigid enough that gravity keeps its shape nearly spherical. Yet the principle is the same. If Earth rotated twice as fast, the equatorial bulge would be much larger. A faster rotation would also reduce surface gravity slightly at the equator and increase it at the poles, exaggerating the difference we already measure today. The precise shape we live on is a record of how rotation and gravity have reached equilibrium over billions of years. Other planets offer variations on this theme. Mars, for example, is smaller than Earth and rotates at nearly the same rate, yet its flattening is less pronounced. Its internal structure is cooler and stiffer, making it more resistant to deformation. Its surface also bears immense features: volcanoes like Olympus Mons and deep valleys like Valles Marineris, that create local deviations far larger than those on Earth. Mars's overall roundness hides these extremes, but measured in relative terms, its surface relief is greater than any on our planet. The largest volcano on Mars rises 22 kilometers above the surrounding plains, nearly 3 times the height of Everest. Yet on the scale of the whole planet, this is still a minor irregularity, a small ripple on a nearly perfect sphere. Venus provides another contrast. Similar in size and density to Earth, it spins incredibly slowly. One rotation takes 243 Earth days, and it turns in the opposite direction. That slow rotation means it experiences almost no flattening at all. Venus is nearly a perfect sphere, shaped only by gravity. Its thick atmosphere smooths temperature differences, distributing heat evenly across the surface, and its lack of significant rotation-driven weather systems makes it one of the most geometrically simple planets in the solar system. Its surface, hidden beneath clouds, reveals no polar compression, no noticeable bulge. It shows that rotation, not mass alone, determines how round a planet appears. Mercury, closest to the Sun, rotates even more slowly, completing 3 rotations for every 2 orbits. Its gravitational field is dominated by the sun's pull, and its shape is a near-perfect sphere as well. But beneath that smoothness lies an extreme. Mercury is dense, with an oversized metallic core that makes up more than half its volume. Its gravity is strong for its size, and that compactness produces a shape tightly bound by its own mass. The lack of an atmosphere or significant tectonic activity has left it largely frozen in time, its form preserved for billions of years. Farther out, the ice giants Uranus and Neptune show a different story. Their rotation periods are short, 17 and 16 hours respectively, and their compositions of water, ammonia and methane under immense pressure make them fluid enough to deform significantly. Both are oblate spheroids, though not as extreme as Jupiter or Saturn. Uranus, with its axis tilted by nearly 98 degrees, presents another curiosity. Its rotation is almost sideways relative to its orbit, meaning its poles point nearly toward and away from the Sun. This tilt causes its shape to interact with sunlight in unusual ways, giving it seasons that last decades. Yet, physically, it remains bound by the same balance between rotation and gravity that shapes every spinning world. Beyond the planets, moons and asteroids show how gravity competes with material strength at smaller scales. The Moon, our nearest neighbour, is round, but not perfectly so. It is slightly elongated, its long axis pointing toward Earth, shaped by tidal forces during its early history. These forces locked it into synchronous rotation, so the same side always faces us. The Moon's equatorial bulge and minor flattening record a time when it spun faster and was pulled by stronger tides. Over billions of years, friction within its interior dissipated energy, slowing its rotation and freezing its shape into the form we see today. Even now, the Moon's mass distribution is uneven, denser on the near side, which affects its orbit and the wobble known as libration. Smaller moons in the solar system show greater irregularities. Many are not round at all but potato-shaped or elongated, held together by their own limited gravity. Saturn's moon Mimas, for instance, is barely large enough to be spherical. Its shape is dominated by a giant crater, giving it an appearance like a dented sphere. Mars's moons, Phobos and Deimos, are irregular chunks of rock, their gravity too weak to pull them into equilibrium. These forms illustrate the threshold of roundness, the point at which size and gravity overcome rigidity. For rocky bodies, that threshold lies around 500 kilometers in diameter. Anything smaller can resist its own gravity and remain irregular. Anything larger must yield and become rounded. Among irregular bodies, asteroids show the most variety. The asteroid Eros is elongated like a peanut, while Itokawa resembles a cluster of rubble. Bennu, one of the most studied asteroids, is shaped like a spinning top, its equator bulging from rotation. These shapes are snapshots of physics on small scales, where cohesion, collisions and rotation all compete with gravity. They are reminders that roundness is not an intrinsic property, but a consequence of scale and motion. Beyond the solid worlds, the contrast becomes even greater. The Sun, like all stars, is nearly spherical because of the immense strength of its gravity, yet even it shows slight flattening from rotation. Measurements show that the Sun's equatorial diameter exceeds its polar diameter by about 10 kilometers, a tiny difference compared to its overall size, but a clear sign that even a star is not perfectly round. Rapidly rotating stars elsewhere in the galaxy show far greater distortions, some bulging so much that they take on an oblate, almost disc-like form. The balance between gravity and rotation, universal and impartial, sculpts every celestial body from the smallest moon to the largest star. When comparing these shapes, one sees that Earth lies comfortably in the middle, large enough for gravity to ensure roundness, solid enough to resist extreme flattening, rotating fast enough to create balance but not distortion. It represents an equilibrium among the possible planetary forms. Its flattening is moderate, its surface irregularities small, its stability remarkable. The presence of oceans and atmosphere adds dynamic complexity, but even they conform to the same principles. The ocean bulge at the equator mirrors the equatorial bulge of the solid planet, both arising from rotation and centrifugal force. The atmosphere too expands slightly outward along the equator, maintaining the same symmetry. Every part of the Earth participates in this shared geometry. In comparing the Earth to other worlds, we also see how composition affects shape indirectly through internal processes. On gas giants, internal convection moves freely, allowing the planet to respond instantly to rotation and tidal forces. On rocky planets like Earth, the crust resists deformation, so adjustments occur over geological timescales through processes like isostasy and mantle flow. This difference means that gas giants appear almost perfectly shaped for their rotation, while rocky planets display small irregularities tied to their history. Mars's volcanoes, Earth's ocean trenches, and the Moon's basins are not signs of imperfection, but records of slow, rigid responses to forces that gas planets handle fluidly. Temperature also plays a role. In colder bodies, materials are stiffer and less responsive to stress. In hotter ones, matter flows more easily. This explains why icy moons can exhibit smooth, spherical shapes, despite being smaller than rocky ones. Pluto, for example, though smaller than our moon, is round, because its ice-rich composition behaves plastically under its own gravity. Its surface can slowly adjust, erasing irregularities over time. Similar processes round off Europa, Enceladus, and other icy moons, where internal heat from tidal flexing allows the surface to flow and settle into equilibrium. Comparing the Earth's shape to that of these worlds reveals that roundness, flattening, and irregularity are not aesthetic differences but physical responses. The degree of flattening indicates how fast a world spins. The level of irregularity shows how strong its materials are. The presence of bulges, ridges, or asymmetries marks where gravity, rotation, and internal dynamics have reached compromise. The shape of a planet is its history made visible, a fossil of forces acting over billions of years. For Earth, that history includes collisions that added mass, the formation of the Moon through a giant impact, the slow cooling of the mantle, and the continuous movement of tectonic plates. Each event left a trace in its shape. The slight offset between the planet's geometric and gravitational centres, the small asymmetries between hemispheres, and the distribution of continents and oceans all testify to its dynamic past. Compared to other planets, Earth's shape is remarkably well balanced, a reflection of long-term stability in its internal and external conditions. If we could line up all the worlds of the solar system by their degree of roundness, we would see a smooth progression, from jagged asteroids to nearly perfect spheres. The dividing line between the irregular and the round corresponds precisely to the strength of gravity versus material rigidity. This boundary is the essence of planetary formation. It marks where matter becomes planet-like, where physics begins to sculpt symmetry from chaos. The Earth sits far beyond that boundary, its mass ensuring that gravity dominates every detail of its form. Yet, within that dominance, subtle variations persist. Mountains rise, trenches sink, ice accumulates, and tides move. The Earth remains round not because it's static, but because these processes are small compared to its scale, and because gravity continually restores balance. The same principle applies across the universe. Wherever matter gathers, gravity strives for equilibrium, and rotation introduces the deviation that makes every world unique. Seen this way, the Earth's shape is not special but exemplary. It demonstrates the universal rules that govern all bodies, while also expressing the local conditions that make our planet distinct. Its moderate rotation, balanced mass, and complex surface give it a geometry that's neither extreme nor simple, a shape of compromise, harmony, and motion. When compared to the flattened forms of Jupiter, the perfect sphere of Venus, or the fractured contours of asteroids, the Earth's oblate, uneven roundness represents the middle ground of planetary form, the point where all competing forces find peace. And beyond the physical comparisons lies something deeper. Through the shapes of other worlds, we glimpse the universality of physics itself. The same gravity that rounds the Earth holds galaxies together. The same centrifugal balance that flattens Saturn shapes spinning stars. The curvature of space-time that defines Earth's gravitational field applies equally to all massive bodies. Every shape in the universe, from the smoothness of gas giants to the jagged irregularity of asteroids, is a consequence of the same simple principles. The Earth's form is just one expression among countless others, each governed by the same equations that tie motion, mass, and energy together. In seeing these comparisons, we understand more clearly that the planet we live on is not defined by perfection, but by balance. Its shape reflects not isolation, but participation in a universal pattern, one where every rotation, every mass, and every force contributes to a shared geometry. And as we look outward from the Earth to the other worlds, we find that the roundness we see is the universe's way of finding stability through motion, the same quiet balance that holds our planet steady as it turns beneath the thin halo of its atmosphere, under the steady curve of space and time that connects it to everything else that spins, drifts, and revolves in the dark. When you look at the Earth from space, it seems complete. The surface curves softly into the distance, fading into light and shadow, surrounded by the faint blue trace of the atmosphere. It is difficult to imagine that such roundness is not static, but the result of balance, a continuous dynamic compromise among gravity, motion, and energy. The planet beneath that smooth horizon is not at rest. It moves, flexes, wobbles, and breathes through processes that span from fractions of a second to billions of years. What appears to be stillness is stability maintained through motion. The shape of the Earth, the shape of home, is not something the planet simply has. It is something it continually becomes. From the ground, we sense none of this. The horizon looks flat, the air feels weightless, the world feels steady beneath us. Yet every moment we stand upon a surface that curves beneath our feet, carried by a rotation faster than any human vehicle could sustain. We are moving with the crust as it drifts on a mantle of slow convection. We are rising and falling by millimeters as the crust flexes under atmospheric pressure, tides, and the pull of the moon. Even the air above us is in motion, flowing with patterns that stretch across hemispheres. These countless motions merge into balance. The planet maintains its shape not by resisting change, but by accommodating it, adjusting in ways so subtle that they form the background of everything we know. The shape we live on, the oblate sphere with mountains, basins, and oceans, is a synthesis of opposing tendencies. Gravity pulls inward, seeking symmetry. Rotation pushes outward, seeking expansion. Heat drives convection from below, while radiation cools the surface from above. The crust shifts to relieve stress. The oceans rise and fall to distribute mass. Each force modifies the others, and the result is the round, slightly flattened, uneven planet that has persisted for more than 4 billion years. No single influence dominates. The Earth's shape is a record of equilibrium, the physical memory of every process that has ever acted upon it. Even the smallest irregularities, the local differences we call landscapes, owe their existence to this balance. A mountain range forms where plates collide, but its height is limited by gravity. An ocean trench forms where crust descends, but its depth is restrained by the buoyancy of rock. Over time, erosion, deposition, and tectonics redistribute material so that the average curvature remains consistent. The surface changes endlessly, but the shape remains the same in principle. The planet's roundness is not an accident, but a consequence of physics expressed over unimaginable timescales. When we measure this shape, with satellites, lasers, and the equations of relativity, we find that it matches the predictions of physics with astonishing precision. The equatorial bulge, the polar flattening, the gravitational variations across continents and oceans all conform to the expectations of motion and mass. Even the smallest deviations can be explained by density differences, rotation, or external forces. The closer we look, the more coherent the picture becomes. The Earth is a system in balance, its shape an ongoing expression of that balance. To see the Earth as a shape is to see it as a whole. Every local irregularity becomes part of a global curve, every detail an aspect of the same structure. The surface we live on is only a small part of that whole, an interface between deeper layers of rock and the vastness of air and space. The mountains and valleys that seem immense to us are minute when compared to the planet's size. If the Earth were reduced to the size of a smooth sphere only a few centimeters across, those enormous mountain ranges would vanish into microscopic texture. It would feel flawless to the touch. This fact is not meant to diminish the surface, but to emphasize how gravity's pull smooths and unifies everything, maintaining a consistent curvature beneath all complexity. The idea that the Earth is round is no longer an abstraction. It is a measured truth, confirmed by every form of observation we possess. Satellites in orbit trace circular pairs defined by its gravity. The horizon curves predictably in every direction. The shadow the Earth casts on the Moon during a lunar eclipse is always round. The physics that explain these facts do not depend on belief or perspective. They emerge naturally from the way matter and energy behave. The roundness of the planet is a direct result of the universe's tendency toward equilibrium, the same tendency that shapes stars, galaxies, and even the smallest droplets of water. From a distance, the Earth's shape becomes a simple outline, but its meaning deepens with understanding. The geoid, the true physical surface defined by gravity, is not perfectly smooth but gently undulating, a reflection of the planet's inner variations. Its curves align with the invisible geometry of space-time, where gravity and time intertwine. The roundness we see is the projection of this deeper structure, where matter shapes space and space guides matter. The Earth curves both outward, as a sphere, and inward, as a field, a dual shape that defines both its presence in the cosmos and the space around it. This curvature extends beyond physics. It connects to the way we experience the world. The idea of home itself depends on stability, on the sense that the ground beneath us endures. Yet that stability is created by continuous motion, rotation, revolution, and the countless smaller movements within. The planet's shape sustains that motion, distributing forces evenly so that the crust doesn't tear apart, the atmosphere doesn't escape, and the oceans don't drift into space. The balance that makes the world habitable is built into its geometry. The curvature of the Earth is not just a mathematical description. It is the condition for life. The atmosphere, thin as it is, follows that curvature exactly. Its layers bend with the planet, spreading the light of the sun across the sky and holding warmth through infrared radiation. The oceans do the same, conforming to the gravitational field, rising and falling with tides but never breaking from their global contour. Even the molten metal of the core moves according to the same curvature, its flow sustaining the magnetic field that extends far beyond the surface, forming another invisible shape, a vast protective cocoon deflecting solar particles and radiation. Every part of the planet, from its deepest layers to its outermost edge, participates in the same balance, following the same curvature of space and time. Seen from orbit, the Earth looks perfect, but that perfection hides texture, small imperfections that carry meaning. The unevenness of its surface, the asymmetry of continents and oceans, the slight offset of the magnetic field from the rotation axis, the fluctuations in gravity and temperature, all of these make the planet alive. Perfect symmetry would mean stillness, and stillness would mean no motion, no change, no life. The Earth's shape, with all its subtle irregularities, is the form of motion sustained over time, the geometry of a living planet. Every planet has its own balance between gravity and motion, but only on Earth has that balance given rise to an atmosphere rich in oxygen, oceans of liquid water, and a surface that cycles through erosion and renewal. Its shape is not just a physical outcome but a framework that allows these systems to exist. The curvature defines how air moves, how water collects, and how sunlight spreads. The gentle flattening at the equator ensures that the rotation distributes heat efficiently. The gravitational field holds the atmosphere while allowing convection. Even the slight tilt of the axis, which contributes to the planet's overall orientation in space, creates the rhythm of seasons. All these conditions are consequences of shape and motion working together. When we compare this balance to other worlds, the uniqueness of Earth's geometry becomes clear. Mars, similar in size but lacking a strong magnetic field, lost much of its atmosphere to space. Venus, nearly identical in radius, rotates so slowly that its equilibrium differs entirely, resulting in a dense atmosphere and extreme surface conditions. Gas giants maintain balance through rotation, but their surfaces are undefined, their shapes more abstract than solid. Among all these, the Earth occupies a middle ground, solid yet dynamic, round yet irregular, massive enough to hold an atmosphere but not so massive that it collapses into uniformity. The shape of home is the shape of compromise, an equilibrium fine-tuned by the universe's simplest rules. Gravity, rotation, and internal heat continue to maintain this equilibrium. The core generates energy that circulates through the mantle drives plate motion, the plates shape the surface, and the surface interacts with the atmosphere. The cycle is continuous, transforming without breaking. Every mountain range, every trench, every current of air participates in the same dynamic balance. The curvature of the Earth, at every scale, is the visible trace of that balance. The geometry of a planet in motion, maintaining its form by constant adjustment. Time adds another layer to this shape. Over millions of years, continents drift, ice sheets grow and recede, and the distribution of mass shifts. Each change alters the gravitational field slightly, and the planet responds. The wobble of its axis, the length of its days, and the height of its seas all adjust in response to how mass moves. Yet through all of this, the roundness remains. The planet's overall shape endures even as every part of it evolves. That persistence, that ability to change without losing equilibrium, defines the stability of Earth's form. If we could watch the Earth from far away over the span of eons, we would see it subtly changing shape. Continents rearranging, poles wandering, the bulge at the equator shifting with rotation. But we would also see that its roundness never disappears. The planet continues to balance itself, its curvature adjusting minutely to keep the whole system stable. This constancy within change is what makes the Earth's shape more than geometry. It is the planet's identity expressed through physics. The shape of home is also a scale of perception. From where we stand, the world feels flat. Our senses evolved within a small range, too narrow to detect curvature directly. The flatness we see is a local illusion, a perspective limited by our size. Only when we step back, through flight, orbit, or imagination, does the curve reveal itself. That realization, once reached, never disappears. It reshapes how we understand not only the planet, but our place upon it. We live on a curved surface, moving constantly, bound by gravity, connected by motion to the stars. Every horizon is part of the same arc. Every step we take follows that arc. Every direction leads across the same continuous curve. In that curve lies a quiet unity. The mountains, the deserts, the oceans, and the cities all share the same center of gravity. No matter where one stands on Earth, down always points toward that center. It's a simple fact, but a profound one. All directions of down converge to a single point. That convergence defines the meaning of the home on a physical level. It ties every place on the planet to the same origin. It means that everything and everyone on Earth is connected through the same field of gravity, held together not metaphorically but literally by the curvature of space shaped by the planet's mass. That connection extends outward. The moon's orbit, the path of satellites, the flow of tides, and the rhythm of time all respond to the Earth's mass and shape. The pull that keeps the oceans from escaping also keeps the moon in its path, the same curvature that bends light and holds air. The Earth is both a participant in larger systems and a system unto itself, shaped and shaping in return. Its balance, maintained through motion, links it to the sun, to the moon, to the rest of the cosmos. The geometry of the Earth is in the end the geometry of belonging. Everything that exists upon it, the air, the water, the living forms, conforms to its curvature, held by the same invisible pull. Its roundness ensures that there is no true edge, no privileged position, no single top or bottom. Every point is part of the same whole. Every direction eventually curves back to where it began. That is not only a feature of space, but of perspective. The realization that we're not standing on the surface of something flat and endless, but on a finite world whose shape connects every place to every other. From this understanding arises a quiet sense of orientation. The shape of the Earth defines the rhythm of the planet, the length of days, the pattern of tides, the gradient of air, the flow of heat. Everything follows from the same curvature. To know this shape is to understand that the stability we depend on, the very feeling of being grounded, comes from motion and balance. The ground is not fixed. It is held in equilibrium by the same forces that guide the stars. The Earth is not simply a place in space. It is an ongoing relationship between gravity, matter, and time. And as the planet continues its turn, the shape that holds it remains constant in principle, though it changes in detail. The wobble of its axis, the drift of its plates, the breathing of its atmosphere, and the slow curvature of space-time around it all continue together, shaping what we call home. Every second, the same physics that curves the cosmos curves the surface beneath us, and we live within that curve, surrounded, supported, and defined by it. To understand the shape of the Earth is to see that it is not just a physical object, but a continuous expression of balance. It is the product of motion, the form of energy in equilibrium, the quiet result of universal laws playing out with perfect patience. Its roundness is a reminder that nothing stands apart from those laws, that even the ground beneath us is part of a large geometry that extends beyond sight, and so as the planet turns through the dark, wrapped in its thin halo of air, tracing its curved path through space and time, it remains what it has always been, balanced, moving, alive, and complete in its roundness, the shape of home sustained by motion that never ends.